Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're going to drift gently into a topic that feels almost impossibly distant, yet intimately connected to everything we know about our place in the universe. The coldest places in existence, where temperatures fall lower than anything you can feel here on Earth, colder than any winter night, colder than the heart of Antarctica, colder than even the quietest, most shadowed corner of your freezer. Before we step into this frozen voyage, I want to ask you something simple, and perhaps a little playful. How cold does it feel where you are right now? Is it a gentle chill, the kind that makes you reach for a blanket, or are you in a room comfortably warmed, untouched by frost? Sometimes, noticing the temperature around you, the way your skin senses the air or your body shifts to accommodate it, reminds us just how relative the concept of cold is, and yet, out in the universe, cold is not merely something to be shivered through. It is a state that governs the formation of stars, the dance of particles, the unfolding of cosmic events, and even the possibility of life as we understand it. If you find this quiet exploration of the universe soothing, calming, or simply a gentle way to let your mind wander after a long day, I would be so grateful if you liked the video, perhaps subscribed, and let this calm corner reach anyone else who might enjoy a peaceful pause. And now, as we settle in, I invite you to slow your thoughts, to feel the gentle stillness of this moment, and together we can step beyond the warmth of familiar air and into a realm where the very notion of temperature stretches into extremes that are almost impossible to imagine. Cold, as we often experience it, is a sensation. We notice it when the air bites our skin, when our breath becomes visible, when water feels suddenly sharp and unyielding. On Earth, we have winters, icebergs, frost-covered mornings, and glaciers that have persisted for thousands of years. These are substantial, commanding, even harsh. But when we talk about the coldest place in the universe, we're entering a scale far beyond anything our bodies can endure. Space, vast and almost perfectly empty, is a near-absolute vacuum, which by itself contains almost no particles to carry heat. Without particles to bump into one another, to transmit energy, there is no way for heat to flow in the way we understand on Earth. This emptiness, though seemingly lifeless, is not without its subtle warmth. Every corner of the universe contains a whisper of radiation, the faint afterglow of the Big Bang itself, bathing the cosmos in a temperature that hovers just above absolute zero. That radiation, called the cosmic microwave background, sets a sort of baseline temperature for space, around 2.7 degrees above absolute zero, or roughly minus 270 degrees Celsius. Even here, where our human senses would detect nothing, and our instruments must be finely tuned to perceive the subtle vibrations of energy, there is an underlying hum, a whisper of heat that persists across the galaxies. Yet, this is only the beginning. There are regions within galaxies, and between them, where temperatures drop even lower, where gas and dust are so sparse and spread out that molecules barely collide, where quantum mechanics and thermodynamics intersect in ways that stretch our imagination. These are the true cold spots of the universe, and they are extraordinary in the way they influence matter, energy, and the birth of celestial bodies. Interstellar clouds, for instance, are massive structures of gas and dust, sometimes spanning dozens of light years, that float silently between stars. Within these clouds, known as molecular clouds, temperatures can drop to just a few degrees above absolute zero. These clouds are far from uniform. They are laced with dense pockets, filaments, and clumps where gravity begins its patient work, slowly pulling material together to eventually form stars. In these regions, the cold is a necessity, not a nuisance. Without such extreme temperatures, gases would expand too violently, pressures would rise, and matter would not coalesce. The very creation of stars depends on the quiet, relentless grip of cold, holding space together, slowing motions enough for gravity to sculpt the beginnings of stellar bodies. Within these clouds, there are even smaller regions known as Bok globules. These are compact, dense, almost shadowy islands of cold, sometimes only a few light years across, where temperature falls even further, creating conditions where atoms move sluggishly, collisions become rare, and molecules freeze onto tiny dust grains. It is within these hidden, frigid pockets that nature experiments, storing material and energy, waiting for the conditions to ignite nuclear fusion and give birth to a new sun. Among the places we know to be truly, almost incomprehensibly cold, one stands out: the Boomerang Nebula. This celestial object, located thousands of light years away, holds the record as the coldest known place in the universe. Its temperature, astonishingly, is only about 1 degree above absolute zero, just a fraction of a degree lower than the cosmic microwave background. The nebula achieves this extraordinary cold because it is an expanding cloud of gas, rapidly moving away from its central star. As the gas expands, it cools in a process not unlike blowing across hot soup to lower its temperature. The Boomerang Nebula is effectively a natural refrigerator on a scale that human imagination struggles to grasp. Here, heat is not just absent, it has been chased away by the dynamics of expansion, leaving behind a region colder than anything achievable in our laboratories for decades, until we began pushing the boundaries of cryogenics and atomic physics. Measuring such extremes of cold is itself a remarkable achievement. Scientists use sensitive instruments capable of detecting faint radiation, analysing the motion of particles, and interpreting spectral lines that shift ever so slightly with temperature. It is a delicate dance of physics, observation, and mathematics, requiring instruments cooled to even lower temperatures than the regions they study, often using liquid helium and advanced refrigeration techniques. In laboratories on Earth, we attempt to replicate conditions approaching absolute zero, achieving temperatures within billionths of a degree from the theoretical limit. In these settings, strange and exotic states of matter emerge: superfluids, Bose-Einstein condensates, materials that behave more like a single quantum entity than individual atoms. These experiments not only allow us to understand the limits of cold, but also provide insight into the behaviours of matter in distant cosmic regions. Absolute zero, the point at which atoms cease almost all motion, marks the limit of cold in classical physics. Yet even here, quantum mechanics ensures that there is still residual motion, a zero-point energy that cannot be removed. It is a reminder that cold is never absolute, even when it approaches a point that seems theoretically unreachable. In the universe, regions near absolute zero are the rule rather than the exception, especially in the vast voids between stars, in dark molecular clouds, and in the spaces that stretch between galaxies. Each of these environments is not only frigid, but also a stage for processes that shape galaxies, regulate star formation, and influence the chemical evolution of the cosmos. Even within our own solar system, we find extreme cold. The outer planets, their moons, and icy bodies like Pluto and Eris exist in shadows far from the Sun, where temperatures can fall to below -230 degrees Celsius. These regions remind us that cold is a relative measure. While we might associate cold with discomfort or stillness, in space it is a necessary condition for matter to behave in ways that allow planets to retain atmospheres, moons to remain icy, and comets to carry water and organic molecules across the solar system. Cold governs structure, stability, and time itself in ways that are subtle but undeniable. And yet, as we trace the presence of cold across the universe, it becomes clear that temperature is more than a simple reading on a thermometer. It is an indicator of energy, motion, and the interplay between matter and radiation, from the Boomerang Nebula to intergalactic space, from the frigid cradles of molecular clouds to the icy surfaces of distant worlds. Cold is woven into the very fabric of the cosmos. It tells a story about the history of the universe, the forces that shaped it, and the processes that continue to unfold, silently, without urgency, without noise, but with remarkable consistency. Each particle that slows, each molecule that freezes onto a dust grain, each photon that escapes into the void contributes to a portrait of a universe in which cold is not absence, but a presence in its own right, a condition that makes stars, planets, and even life possible. The coldest places in the universe invite reflection. They remind us of the fragility and resilience of matter, the patience of physics, and the astonishing scale on which processes operate. They connect the extremes of the cosmos to our own experience of temperature, of warmth, and of the comfort of blankets and fireplaces, highlighting just how relative these sensations are. When we consider a nebula hovering at just 1 degree above absolute zero, it becomes easier to appreciate the delicate balance that allows our planet to support life at temperatures that feel natural to us, even if they are high compared to cosmic standards. Cold is, in this sense, both a scientific reality and a lens through which to understand our place in the universe. So as we linger in thought, imagining these unimaginable temperatures, from the emptiness between galaxies to the icy outskirts of our solar system, from dark molecular clouds to the singular chill of the Boomerang Nebula, it becomes clear that cold is more than discomfort, more than winter nights or frosted windows. It is a governing force, a gentle guide, a condition that shapes existence, patterns matter, and defines the very processes that bring the universe into being. And while our human senses are incapable of truly feeling these extremes, our minds can perceive, our instruments can measure, and our imagination can drift across the silent, frozen expanses, connecting warmth to cold, presence to emptiness, and life to the vast, frigid voids that surround us. When we speak of cold, it is often easiest to begin with what we know, the sensations and experiences closest to our daily lives. Step outside on a winter evening and feel the crisp air tug at your cheeks. Notice how the breath becomes visible, curling like gentle mist before fading into the dark sky. The temperature might be just a few degrees below freezing, but it is enough to make you wrap your coat tighter, pull your scarf higher, or stamp your feet for warmth. Cold in this sense is immediate, tactile, and familiar. It shapes our behaviour, our comfort, and even the way we perceive time, as a long, bitter walk in December can seem to stretch endlessly, while sitting near a fire reading a book makes the hours vanish in quiet contentment. These sensations are subjective, influenced by attention, expectation, and our own physiology. Yet, they form the first step in understanding cold, a bridge between human experience and the extremes we will explore beyond our planet. Our personal encounters with cold remind us that temperature is not simply a number. It is a force that interacts with life, energy, and the environment. On Earth, the coldest regions offer a tangible measure of how low temperatures can go while still allowing some form of life to persist. Take, for instance, the vast icy expanses of Antarctica, where temperatures regularly drop below -50 degrees Celsius and can fall further still during the winter months in interior regions. Here, the wind carries sharp gusts that seem to cut through clothing, and the sun, low on the horizon, casts long, pale shadows across an unbroken field of ice. Even in these conditions, life finds a way. Microbes exist within frozen lakes beneath kilometers of ice, resilient in the face of extreme pressure, darkness, and cold. Birds and seals adapt with thick layers of insulation, specialized blood flow, and behavioral strategies to conserve energy. These extremes offer a model, a way of understanding cold not as a barrier but as a condition that shapes adaptation, persistence, and survival. The Antarctic chill, while harsh, is moderated by context. The region is bounded by geography, influenced by the presence of the ocean, sunlight, and seasonal variation. Even so, it represents a level of cold that challenges human endurance, offering a first glimpse at the kinds of conditions that exist elsewhere in the universe on scales far beyond what we can directly experience. The cold we encounter on Earth is affected by the movement of air, water, and radiation. Winds carry heat away from surfaces, humidity alters the perception of temperature, and snow, with its high reflectivity, interacts with sunlight to influence the surrounding environment. These effects, though complex, are tangible. Standing on a snowy plain, feeling the sharp gusts of Antarctic wind, we experience firsthand the interplay of temperature, environment, and energy. Yet even here, temperatures are mild compared to what exists in deep space or within certain nebulae, where atoms move with a lethargy that our senses cannot detect, and where heat has been stripped away nearly completely. The extremes of cold in familiar environments prepare us, in a way, to appreciate the far stranger and more absolute cold that dominates the interstellar void. Winter nights in more temperate regions provide a similar, if smaller, scale for understanding. A frosted window pane, a breath that condenses into visible mist, the sensation of skin cooled by a gentle wind. These experiences are small reminders that energy is being transferred, that molecular motion is slowing, and that the environment has the power to influence the body and mind. Our perception of cold is deeply psychological as well as physical. Standing in a winter street under streetlights, waiting for a bus, we notice how attention sharpens, how moments stretch, how the mind marks time differently. These subjective experiences of cold, in combination with measurable temperature, give a rich, layered understanding of what it means for an environment to be cold. They also highlight the importance of context. 10 degrees below freezing can feel tolerable if one is dressed appropriately, immersed in movement, or accompanied by friends, but the same temperature may feel insufferable if we're still, unprepared, or alone. Similarly, the coldest places in the universe are defined not only by temperature, but by the density of particles, the intensity of radiation, and the forces acting upon matter. Consider high-altitude locations on Earth, where temperature decreases with elevation. As climbers ascend peaks such as Mount Everest, the air becomes thinner, drier, and colder, reaching averages well below -30 degrees Celsius near the summit during winter months. The human body must compensate in real time, generating heat internally, adjusting circulation, and regulating breathing. In these environments, cold is no longer just an inconvenience. It is a dominant factor, shaping behavior, physiology, and survival. The patterns of heat loss, the role of insulation, and the strategies employed to withstand extreme cold on Earth provide valuable analogies for understanding how matter behaves under the near absolute zero conditions found in molecular clouds or nebulae. Even though the scales differ dramatically, the principles of energy transfer, motion, and thermodynamics remain the same. In Antarctica, the interior plateau provides an environment that comes closest on Earth to the stillness and emptiness of space, though it is bounded by atmosphere and sunlight. During the long polar night, temperatures can drop below -80 degrees Celsius. Wind speeds can exceed 100 kilometers per hour, and the sun may not rise for months. The landscape is dominated by ice sheets, snow dunes, and crevasses that stretch endlessly into the horizon, creating a stark, almost abstract environment where survival is a careful negotiation between body, environment, and tools. Researchers working in these regions must account for the extreme cold in every aspect of life, from clothing and shelter to food and communication. In many ways, Antarctica serves as a proxy for understanding how matter behaves under frigid conditions, providing a laboratory that, while still vastly warmer than interstellar space, captures some of the essential dynamics of extreme cold: slowed chemical reactions, reduced molecular motion, and enhanced stability of materials that would otherwise degrade rapidly at higher temperatures. Cold also influences the physical structure of the environment itself. Ice, snow, and frost are not merely passive indicators of low temperature. They shape terrain, direct flows of water, and influence geological processes over time. Crevasses and glaciers form in response to stress and temperature gradients. Frost heaving lifts soil and rock, and permafrost preserves organic material for millennia. These processes illustrate how cold interacts with matter, reorganizing it in ways that are both slow and relentless. In a similar sense, the coldest regions of space act upon gas and dust, guiding their aggregation into dense clouds, shaping the formation of stars and controlling the chemistry that leads to the creation of complex molecules. Cold, whether on Earth or in deep space, is never simply an absence of heat. It is an active agent, shaping matter and energy in ways that are subtle, profound, and measurable. Our familiarity with winter, chill, frost, and icy landscapes gives us an intuitive sense of how low temperatures affect living systems, human behavior, and material properties. It also provides a bridge to the cosmic scale. Just as Antarctic researchers must adapt to extreme cold through clothing, shelter, and careful planning, matter in space follows the rules dictated by low temperature, responding to forces that are otherwise negligible in warmer environments. Particles move sluggishly, gases condense, radiation dominates, and chemical reactions slow dramatically. The fundamental principles of thermodynamics operate, but their effects are amplified to degrees that would be impossible to replicate without highly specialized laboratory equipment. Understanding familiar cold gives context to the extremes we will soon explore, allowing the mind to stretch from the tactile chill of a winter night to the near absolute zero that defines the coldest corners of the universe. Even within human habitations, cold shapes experience in ways that echo cosmic principles. Refrigerators and freezers, insulated homes, and controlled laboratory environments create microcosms of extreme temperature. Food is preserved, biological samples remain viable, and experiments can explore the behavior of matter under carefully controlled low-temperature conditions. These engineered spaces, while far from the extremes of space, illustrate the same principles at work. Lower temperatures reduce molecular motion, slow chemical reactions, and stabilize matter. When we consider the Boomerang Nebula, dark molecular clouds, or intergalactic voids, the same rules apply, but scaled across immense distances and timescales. Cold governs structure, stability, and evolution, whether in a laboratory freezer or in the depths of the universe. In the southern polar regions of our planet, the human experience of cold is also profoundly temporal. Temperatures fluctuate over days, weeks, and months, influencing sleep, metabolism, and daily activity. Our circadian rhythms, internal clocks, and behavioral patterns are subtly influenced by seasonal temperature variation. Similarly, in space, cold is not uniform or static. Molecular clouds, for instance, may experience localized heating due to nearby stars, shock waves, or cosmic radiation, creating pockets of relative warmth amidst extreme cold. Temperature gradients emerge, influencing the flow of matter, the formation of stars, and the chemical reactions that occur within these regions. Cold is therefore not only a condition but a dynamic variable, interacting with other forces to shape the universe in measurable ways. Even our language and perception of cold reflect the diversity of experience. Terms like freezing, icy, frigid, or arctic evoke different intensities, durations, and contexts. On a winter night, a cold breeze might be invigorating, while the interior of an Antarctic ice shelf can be dangerous without proper equipment. This relativity mirrors the way scientists describe cold in space. A few degrees above absolute zero may seem inconceivably cold to us, yet it is only one fraction of the scale that stretches from our sun-warmed planet to the Boomerang Nebula and beyond. Understanding familiar cold, therefore, is not only a matter of comfort, but also a conceptual framework, a way to anchor imagination and measurement as we explore the extremes of the cosmos. And so, as we think about the chill of winter nights, the frozen deserts of Antarctica, and the frost that coats lakes and rivers, it becomes clear that cold is far more than a simple sensation. It is a measure of energy, a determinant of behaviour, and a shaping force in both biology and physics. The cold we know provides a window into the cold we cannot experience directly, offering lessons about the way matter responds, how energy is distributed, and how systems evolve when heat is scarce. Beyond the familiar chill of winter nights and the frozen expanses of Antarctica, cold takes on a scale that is both humbling and almost impossible to fully grasp. Space, in its vast emptiness, stretches endlessly in all directions, a seemingly infinite expanse of darkness and stillness, where the concept of temperature becomes something entirely different from the warmth or chill we feel here on Earth. The void between stars is not simply cold in the way we might imagine. It is a near absolute absence of heat, a realm where atoms drift in silence, radiation pulses faintly across unimaginable distances, and matter behaves in ways that our daily experience cannot anticipate. Standing at the edge of human understanding, one realizes that cold in space is not merely an absence, but a defining condition, shaping the formation of galaxies, stars, planets, and the very processes that govern the cosmos. In space, temperature is a measure not of human comfort, but of the energy of particles, their motion, and the radiation that permeates the vacuum. Unlike the air in a room, or the atmosphere around a planet, the interstellar medium is extraordinarily sparse. A single cubic centimetre may contain only a few atoms, sometimes even less. With so few particles to interact, there is little opportunity for heat to transfer, for collisions to occur, or for energy to spread in ways familiar to us. In such an environment, matter is often colder than any naturally occurring temperature on Earth, approaching the theoretical limits defined by absolute zero. The cosmic microwave background radiation, a remnant of the Big Bang, provides a baseline temperature of about 2.7 Kelvin, roughly minus 270 degrees Celsius. This is the faint hum of heat that fills the universe, barely perceptible, yet present even in the deepest voids, a reminder that cold is never absolute, even on the larger scales. The seeming emptiness of space is deceptive. While it may appear silent, inert, and static, it is in fact a complex network of forces, particles, and radiation fields. Even the void is populated by cosmic rays, photons, and occasional dust grains that move slowly, interacting in subtle ways. These interactions are not violent or energetic by terrestrial standards, but over vast timescales, they influence the distribution of matter, the formation of molecular clouds, and the chemical evolution of galaxies. Cold in this context is not just the absence of warmth, it is a parameter that governs the behaviour of everything, a quiet hand that slows motion, stabilises structures, and dictates the timing of cosmic events. Consider the scale of distances involved. Stars are separated by light years. Regions of space between galaxies span millions of light years, and yet within these immense stretches, the rules of thermodynamics apply just as they do in a cup of water or the ice covering a pond. At the interstellar scale, temperatures can vary dramatically, depending on local density, radiation exposure, and chemical composition. Dense molecular clouds, where stars are born, can cool to a few degrees above absolute zero, while nearby stellar nurseries may experience localized heating from young, bright stars. Even here, the balance of heating and cooling is delicate. Radiation warms matter, but expansion, emission, and sparse collisions ensure that temperature remains extraordinarily low compared to our everyday experience. The void itself becomes a canvas upon which matter, energy, and time interact in the slow, measured rhythm dictated by extreme cold. This extreme cold shapes the formation of structure in the universe. Without it, molecular clouds could not collapse under their own gravity to form stars. Without cold, gases would remain diffuse, motion too vigorous for aggregation, and the processes that lead to planets, moons, and eventually life would be hindered. The universe, in a sense, relies on its cold regions to organize itself, to create order out of apparent emptiness. Just as the frozen ground of Antarctica preserves material and slows change, the frigid vacuum of space stabilizes matter, allowing slow, precise processes to unfold over millions and billions of years. Temperature, or the lack thereof, becomes a key variable in the story of cosmic evolution, influencing everything from chemical reactions to the movement of dust grains, to the eventual ignition of nuclear fusion within collapsing stellar cores. Even in the emptier stretches of space, radiation is never truly absent. Photons drift across billions of kilometers, occasionally encountering a particle, nudging it slightly, transferring an infinitesimal amount of energy. This interaction, though rare, prevents the universe from reaching absolute zero and ensures a faint, persistent warmth in the form of the cosmic microwave background. It is a subtle but essential reminder that cold is not merely a measure of absence, but a dynamic equilibrium between motion, energy, and radiation. The vast void, then, is not uniform. It contains gradients, pockets, and variations that define the distribution of matter and energy throughout the cosmos. Temperature is not a single number, but a tapestry of conditions, each affecting the behavior of matter on scales both vast and minute. Our understanding of cold in space relies on both observation and inference. Telescopes sensitive to infrared, microwave, and sub-millimeter wavelengths allow scientists to measure temperatures in regions far beyond our solar system. By analysing the emission of molecules, the movement of gas, and the absorption of radiation, we can estimate temperatures that would otherwise be impossible to detect. The Boomerang Nebula, for instance, has been identified as the coldest known place in the universe precisely because of the subtle radiation emitted by its expanding gas. Instruments measure the faint vibrations, the spectral shifts, and the interactions of particles, translating these data into temperature readings that stretch human comprehension. Even here on Earth, laboratories replicate similar conditions using advanced cryogenic techniques, creating environments just fractions of a degree above absolute zero to study the behavior of matter in extreme cold. Cold in space also has consequences for chemistry and molecular formation. In molecular clouds, low temperatures allow hydrogen, carbon monoxide, and other simple molecules to stick to dust grains, freeze into icy mantles, and participate in reactions that would be too slow or impossible at higher temperatures. These reactions form the building blocks of more complex molecules, including organics that eventually seed planets with the ingredients for life. Temperature dictates reaction rate, stability, and the very possibilities of chemistry in these extreme regions. The universe, in this sense, is a laboratory, and cold is the defining condition that enables reactions to proceed at a pace suited to cosmic time. Even human perception of space as cold is shaped by imagination and measurement. We cannot feel these temperatures directly, but we can understand them through analogy, instruments, and careful calculation. Standing on the frozen Antarctic plateau gives a sense of exposure and endurance, but the vacuum of space dwarfs these experiences. There, atoms move with infinitesimal speed, radiation is faint, and energy exchanges are minimal. Particles drift across light years without colliding. A single photon might travel millions of years before interacting with matter. In such conditions, cold is not discomfort but a structural principle, the baseline upon which the universe organizes itself, guiding the formation of stars, galaxies, and planets. Even within this vast icy void, there are variations. Regions near stars or clusters of stars experience localized heating. Radiation from young, hot stars can warm surrounding gas, creating bubbles of slightly higher temperature within molecular clouds. Supernovae inject energy, disturbing the equilibrium, and cosmic rays impart small amounts of energy as they travel through space. Yet, in the interstellar medium at large, temperatures remain extraordinarily low, only rising when energy is deposited locally. The interplay between extreme cold and intermittent heating shapes the universe, creating gradients, structures, and processes that are essential to cosmic evolution. The vastness of space also demonstrates that cold is not merely a human sensation, but a principle of physics at its most fundamental level. Thermodynamic laws apply just as rigorously in near-empty voids as they do in laboratories on Earth. Energy flows, motion occurs, and particles behave predictably according to well-understood physical rules. Cold, in this context, is a measure of these processes, a reflection of the interplay between energy, matter, and radiation. The emptiness itself is structured by temperature, and even in regions that seem inert, the principles of cold dictate the behavior of particles, the aggregation of matter, and the emergence of complex structures over time. Even within our solar system, the void of space exerts its cold influence. The outer planets, icy moons, and distant dwarf planets exist in regions where sunlight is weak, ambient temperatures are near absolute zero, and energy must be carefully balanced for structures to persist. Comets, asteroids, and Kuiper belt objects preserve frozen volatiles, organic molecules, and other materials precisely because cold slows molecular motion, stabilizes matter, and preserves conditions across billions of years. The principles observed in these regions echo those in molecular clouds, the Boomerang Nebula, and intergalactic space. Cold is a constant guiding structure, and ensuring that processes unfold slowly, predictably, and with remarkable consistency. Even as we contemplate this vast icy void, it is important to remember that cold is relative and context-dependent. The same temperature that is deadly to a human being is a normal condition for interstellar molecules. What seems extreme to us is moderate for the universe. The void of space, with its nearly zero particles, faint radiation, and minimal energy transfer, is not hostile by accident. It is the environment in which cosmic processes are calibrated, matter forms stars, and galaxies evolve. The universe, in this sense, is a vast interplay of cold, gravity, radiation, and matter, with temperature serving as a silent regulator of motion, chemical reactions, and structural stability. So as we drift across the emptiness between stars, through the silent corridors that stretch between galaxies, through the dark, frigid molecular clouds where atoms barely move, we begin to understand that cold in space is not merely the absence of warmth. It is a defining characteristic of the cosmos, a principle that shapes the evolution of matter, governs chemical reactions, and preserves the conditions necessary for the slow unfolding of celestial processes. The void is vast, silent, and icy, but within it, structure emerges, stars form, and matter is shaped by the quiet authority of extreme cold. As we float farther from the familiar warmth of planets and stars deeper into the void of space, there exists a pervasive, almost imperceptible glow, a faint whisper from the earliest moments of the universe. This is the cosmic microwave background, often referred to as the afterglow of the Big Bang, a relic of the time when the universe was young, hot, and dense, yet already beginning the long, patient process of expansion and cooling. It is the quiet hum of heat that persists even in the emptiest regions of space, a baseline temperature of roughly 2.7 Kelvin, just a fraction above absolute zero. At first glance, this temperature may seem inconsequential, almost irrelevant, but it represents the echo of a universe that has been expanding, stretching, and evolving for nearly 14 billion years. Every photon of this background radiation is a messenger from a distant past, carrying with it information about the conditions of a universe that was once unimaginably small, dense, and incandescent. The cosmic microwave background, or CMB as scientists call it, is not visible to the naked eye. Unlike sunlight or the warm glow of a fire, it exists in the microwave region of the electromagnetic spectrum, far beyond the colours our eyes can detect. To perceive it, we rely on specialized instruments, satellites, and radio telescopes capable of detecting faint signals across the entire sky. The CMB is remarkably uniform, a nearly constant bath of radiation that envelops everything, yet it contains subtle fluctuations, tiny variations in temperature and density that reveal the seeds of structure in the cosmos. These fluctuations are the imprints of processes occurring when the universe was just a few 100,000 years old, long before stars, galaxies, or planets had formed. They are the blueprint of the large-scale structure we observe today, frozen into the cold fabric of space and time. Temperature in the context of the cosmic microwave background is fascinating because it represents energy in its most diffused form. Each photon carries a minuscule amount of energy, just enough to interact occasionally with atoms or dust particles. These interactions are exceedingly rare, yet over billions of years they have shaped the evolution of matter and the universe itself. The CMB is both a measure of extreme cold and a reminder of the universe's fiery origin. Billions of years ago, these same photons were part of an intensely hot plasma, a glowing sea of light and matter, moving, colliding, and exchanging energy in a universe that was opaque to radiation. As expansion progressed, the universe cooled, matter coalesced, and photons decoupled from particles, travelling freely across space, losing energy and shifting into the microwave spectrum. What was once overwhelmingly hot became faint and cold, yet persistent, a cosmic memory etched into every corner of the universe. In many ways, the CMB is the ultimate measure of cosmic cold. It defines a temperature floor for the universe, the baseline against which everything else is measured. Even in the darkest, emptiest regions of space, far from stars and galaxies, the temperature rarely drops below this limit. In this sense, cold in the universe is not uniform or absolute. It is relative to the persistent presence of this radiation. The afterglow of the Big Bang ensures that no matter how empty a region may appear, there is always a trace of energy, a faint warmth, a signal that the universe is alive in the sense of motion and structure, even where matter is sparse. The cosmic microwave background is more than a static temperature. Its subtle variations detected by missions such as COBE, BUMAP, and Planck reveal a universe that is dynamic, structured, and evolving. Tiny anisotropies in temperature correspond to differences in density in the early universe, which over billions of years grew into the cosmic web of galaxies, clusters, and voids that dominate the large-scale structure of space today. Cold, in this context, is intertwined with motion, expansion, and gravitation. The very faintness of the CMB, its frigid temperature, is what allows these early imprints to remain discernible, preserved against the vast backdrop of cosmic evolution. It is a window into a past that we cannot directly observe, a time before stars illuminated space, when energy was spread across a nearly uniform plasma, and when temperature was the driving parameter in shaping the behaviour of matter. The way scientists study the CMB involves careful measurement of microwave photons that have travelled billions of years. These photons have cooled with the expansion of the universe, their wavelengths stretched, their energies diminished. By mapping the distribution of these photons across the sky, researchers can reconstruct the density variations of the early universe, determine its geometry, and measure fundamental parameters such as the rate of expansion, the composition of matter, and the relative amounts of dark matter and dark energy. Temperature, in this case, is not just an abstract measure. It is a key to understanding the physical laws that govern the universe, the initial conditions that gave rise to galaxies, and the processes that have unfolded over cosmic time. Cold, then, is not an absence but a tool, a property that carries information, guides structure, and enables prediction. Even at a baseline of 2.7 Kelvin, the CMB has practical consequences for the formation of matter. gas clouds, dust, and molecules in the interstellar medium interact with this radiation. Cooling occurs as energy is radiated away, allowing denser regions to form, and extreme cold is maintained despite the presence of sparse heating sources. Without the background temperature of space, matter would behave differently. Photons contribute to the balance of energy in molecular clouds, influence the rate at which atoms collide and stick, and affect the chemical pathways that eventually produce complex molecules. Cold, in this sense, is not inert. It is an active participant, influencing motion, structure, and the potential for star and planet formation. The afterglow of the Big Bang also connects us to the scale of human understanding. Temperatures of a few degrees above absolute zero are difficult to conceptualize, yet they dominate the vast majority of the universe. While Earth, Antarctica, and the outer planets present extreme cold in ways we can measure and even experience indirectly, the CMB represents a nearly universal baseline, a cold that is intrinsic to space itself. It is pervasive, constant, and enduring, a gentle hum that has persisted for billions of years, defining the conditions of the cosmos, shaping the evolution of matter, and providing the reference against which the coldest regions of space can be understood. Even the faint warmth of the CMB can be measured in terms of motion. Photons in the microwave background exhibit tiny Doppler shifts due to the motion of galaxies, clusters, and the observer. These shifts allow scientists to infer velocities, large-scale flows, and the dynamics of cosmic structures. In this sense, cold is not synonymous with inactivity. It is a condition that interacts with motion, providing the canvas on which the dynamics of the universe are painted. Every region of space, even the emptiest void, is embedded in this background, influenced by its presence and shaped by its subtle energy. The cosmic microwave background also reminds us of time. It is both ancient and enduring, a snapshot of the universe as it was nearly 14 billion years ago. Its temperature is a record of expansion, a reflection of how energy has dissipated over billions of years. Cold, in this context, is a measure of history, a persistent echo that carries information about the origins of galaxies, stars, and planets. It is a universal signal, a quiet witness to the evolution of matter, and a guide to understanding the processes that continue to unfold across the cosmos. Even as we contemplate this faint radiation, it is worth remembering that cold is relative. The CMB sets a baseline, but temperatures can fall even lower in specific regions, such as rapidly expanding nebulae or dark molecular clouds. The Boomerang Nebula, for instance, dips below the temperature of the CMB, demonstrating that while cold is universal, it is not uniform. Variations emerge from local conditions, the behavior of matter, and the dynamics of expansion. Temperature, then, is a property of both the universe at large and the specific environments within it, a measure that is simultaneously global and local, faint yet influential, pervasive yet variable. Our own instruments, designed to detect this faint afterglow, must be cooled to temperatures below that of the CMB itself. Satellites and telescopes are chilled to minimize interference, allowing them to detect the subtle fluctuations that reveal the early universe. In this way, human understanding mirrors the conditions of space. To measure extreme cold, we must create even colder conditions locally, approaching the same principles that govern the cosmos itself. Cold, therefore, is both a property of the universe and a challenge for human observation, requiring ingenuity, precision, and patience. The cosmic microwave background is more than a temperature measurement. It is a story written in cold, a narrative of the universe's earliest moments preserved across time and space. It connects the initial hot plasma of the Big Bang to the cold, expansive voids we observe today. It defines the framework within which matter condenses, structures emerge, and stars and galaxies form. Even in the vast emptiness, cold is not absence but structure, a condition that informs everything from chemical reactions to gravitational collapse, from molecular formation to the evolution of entire galaxies, As we consider the CMB, we begin to understand that cold is not merely discomfort or the absence of warmth. It is a baseline, a fundamental parameter of the universe, a silent influence that shapes motion, energy, and matter across incomprehensible distances and timescales. From the frozen plateaus of Antarctica to the icy depths of molecular clouds, from the emptiest voids between galaxies to the faint afterglow of the Big Bang, cold is everywhere, guiding, preserving, and structuring the cosmos. It is quiet, patient, and pervasive, a constant companion in the story of existence, stretching from the earliest moments of the universe to the intricate structures we observe today. Beyond the gentle hum of the cosmic microwave background, beyond the faint afterglow of a universe that has been cooling for billions of years, there exist regions where cold becomes more than a baseline. It becomes a defining condition, a force shaping matter in both subtle and profound ways. These are the interstellar clouds, vast stretches of gas and dust drifting silently between the stars, cradles of frigid matter where temperatures can fall to just a few degrees above absolute zero, and where the slow dance of molecules and atoms begins to orchestrate the next generation of stars. When we think of these clouds, it is easy to imagine emptiness, darkness, and silence. Yet within them, processes unfold that are essential to the life cycle of the cosmos. The cold is extreme, the motion is slow, and time stretches in ways that are almost inconceivable compared to our daily experience. Interstellar clouds, sometimes called nebulae in their broader sense, consist primarily of hydrogen, the simplest and most abundant element in the universe, with traces of helium and heavier elements. These clouds vary widely in density, size, and structure. Some are diffuse, containing only a few particles per cubic centimetre, barely enough to measure with the most sensitive instruments. Others, denser and more compact, allow gravity to begin the patient work of gathering matter into clumps that may eventually ignite as stars. Temperature within these clouds is a crucial factor. Too warm, and gas pressure resists gravitational collapse, preventing star formation. Too cold, and molecular motion slows to the point that collisions necessary for chemical reactions become rare. Cold, in these clouds, is not merely a condition. It is a regulator, controlling the very evolution of matter over millions of years. In the coldest regions of interstellar clouds, known as molecular clouds, temperatures can reach as low as 10 Kelvin, a mere fraction above absolute zero. At these extremes, hydrogen molecules move sluggishly, collisions between atoms are infrequent, and chemical reactions proceed at glacial rates. This slow environment, however, is precisely what allows for the formation of complex molecules. Atoms stick to dust grains, freeze, and interact over long periods, forming compounds that may eventually seed planets with the ingredients necessary for life. The cold acts as a stabilizing agent, preserving these fragile compounds against the disruptive forces of radiation, shock waves, and turbulence. It is a remarkable testament to the role of extreme temperature in shaping the chemical and physical structure of the universe. Even within molecular clouds, temperature is not entirely uniform. Denser regions, where gravity has pulled more matter together, may be slightly warmer due to compression, while more diffuse areas remain colder. Embedded young stars can heat surrounding gas, creating pockets of higher temperature amidst the extreme cold. Yet overall, these clouds are dominated by frigid conditions. Observing them requires instruments sensitive to far infrared and microwave radiation, capable of detecting the faint signals emitted by molecules moving so slowly that their thermal energy is almost imperceptible. In these silent, frigid expanses, cold is both a measurable quantity and a subtle force guiding the arrangement of matter, the initiation of chemical processes, and the eventual collapse into protostars. Interstellar clouds are also remarkably dynamic, despite the low temperatures. Turbulence, magnetic fields, and gravity interact in complex ways, creating filaments, knots, and clumps of matter that stretch across light years. These structures are not immediately apparent to the eye, but their presence is crucial in shaping star formation. Filaments channel matter into denser regions, while magnetic fields can inhibit or redirect gravitational collapse, influencing the final distribution of mass in emerging stars. Cold, in this context, is a slow-motion stage upon which these forces act, a steadying presence that ensures processes unfold gradually, allowing the intricate balance of forces to create ordered structures from seemingly chaotic motion. The chemical composition of interstellar clouds is also profoundly affected by cold. At temperatures just above absolute zero, atoms and molecules have insufficient energy to escape from dust grains once they adhere. This adherence allows chemical reactions to proceed in ways impossible at higher temperatures, forming molecules such as water, ammonia, methanol, and even complex organic compounds. Over millions of years, these molecules accumulate, providing a rich chemical reservoir for the formation of new stars, planetary systems, and potentially life itself. Cold, therefore, is not passive. It is a facilitator, enabling chemistry, structure, and evolution to occur on a scale and over timescales that defy human perception. Observing interstellar clouds also challenges our perception of what cold means. The temperature may be just a few degrees above absolute zero, yet within these clouds, particles still move, photons still traverse vast distances, and subtle energy exchanges occur constantly. Cooling mechanisms are essential. As gas emits radiation, it loses energy, further lowering its temperature and allowing gravitational collapse to proceed. These processes are delicate, dependent on density, composition, and the presence of radiation sources nearby. The cold is not absolute. It is a balance, a dynamic condition that allows matter to organize and evolve over millions of years, shaping the structure of the galaxy itself. Even in our own galaxy, interstellar clouds span incredible distances. Some stretch across dozens of light years, containing hundreds of thousands of solar masses of gas and dust. Within them, temperatures remain extraordinarily low, yet subtle gradients exist, guiding the distribution of matter and the initiation of star formation. Observations using radio and sub-millimeter wavelengths reveal these structures, mapping filaments, knots, and voids, allowing scientists to infer the physical conditions, chemical composition, and thermal properties of these cold regions. The interplay of cold and structure demonstrates that temperature is not simply a number. It is a key variable influencing matter on scales that dwarf human comprehension. The slow pace of chemical reactions within these clouds also highlights the relationship between cold and time. At a few degrees above absolute zero, reactions that would occur in seconds at room temperature may take thousands or millions of years. The extreme cold stretches the timeline of chemistry, creating conditions in which molecules can survive long enough to interact, combine, and participate in processes leading to star and planet formation. In this sense, cold is a kind of temporal regulator, controlling the rate of change, ensuring stability, and providing the necessary conditions for evolution across vast spans of space and time. Even though interstellar clouds are frigid, they are not entirely isolated. Cosmic rays, faint radiation from distant stars, and occasional shock waves from supernovae interact with the gas and dust, injecting small amounts of energy into the system. These interactions can induce localized heating, trigger chemical reactions, or create motion within the cloud. Yet the overall temperature remains extraordinarily low, demonstrating the resilience of cold as a dominant environmental condition. Cold is both persistent and influential, shaping the behavior of matter while allowing for localized variations that drive complexity. Interstellar clouds also serve as laboratories for understanding the extremes of cold. By studying these regions, scientists can observe how matter behaves near absolute zero, how molecules form and survive, and how structures develop under conditions that are impossible to replicate fully on Earth. While laboratory experiments using cryogenic techniques allow us to approach similar temperatures, the scale, duration, and complexity of processes in molecular clouds far exceed anything achievable in controlled settings. The cold of interstellar clouds is, in a sense, a natural experiment, revealing the fundamental properties of matter and energy under extreme conditions. The clouds themselves are often invisible in ordinary light. They are detected primarily through the radiation they emit or absorb, particularly in the infrared and microwave ranges. Dense regions block background light, appearing as dark silhouettes against brighter stars, while other areas glow faintly due to the energy of molecules transitioning between states. Even in the absence of visible light, these clouds are rich with activity, chemical reactions, and structure, all governed by their frigid temperatures. Cold allows these regions to maintain coherence, preserve complex molecules, and slowly guide the formation of stars and planetary systems. As we consider these clouds, it becomes clear that cold is not merely a backdrop. It is an active agent, shaping the organization of matter, regulating chemical reactions, and enabling processes that span millions of years. From the subtle motion of atoms to the collapse of gas into protostars, the extreme cold of interstellar clouds is both facilitator and governor, ensuring that the universe evolves in an orderly, measurable, and predictable fashion. The vast emptiness between stars is not devoid of purpose. It is filled with the quiet authority of cold, a condition that makes cosmic creation possible. Even as we reflect on the scale, density, and structure of interstellar clouds, it is important to remember that their coldness is relative to the human experience. Temperatures just a few degrees above absolute zero are incomprehensible to our senses, yet they are essential for the processes that lead to the formation of stars, planets, and eventually life. The clouds demonstrate that extreme cold is not merely absence, but a necessary and enabling condition, one that organizes matter, preserves chemical complexity, and guides the evolution of the cosmos over incomprehensible spans of time. In these vast frigid expanses, matter exists in a delicate balance. Gravity slowly draws atoms together, radiation removes energy, and cold maintains the structural integrity of the cloud. Over millions of years, dense regions form, collapse, and ignite as protostars, giving rise to the next generation of stars and planets. The cold is both silent and insistent, shaping the destiny of matter in ways that are imperceptible in the moment, but monumental on cosmic timescales. It is the quiet sculptor of galaxies, the patient regulator of chemistry, and the invisible architect of celestial structure. In contemplating interstellar clouds, we can begin to appreciate the full scope of cosmic cold. It is pervasive, essential, and deeply influential. Cold in these clouds is not simply a number on a thermometer. It is a principle that governs motion, chemistry, structure, and the evolution of the universe itself. It is a reminder that even in silence and darkness, order emerges, structure forms, and the universe unfolds according to principles that are measurable, predictable, and awe-inspiring. Within the vast reaches of interstellar space, among the drifting clouds of gas and dust, there exist denser regions known as molecular clouds. These are the coldest, most enigmatic cradles of star formation, regions where temperatures drop to just a few degrees above absolute zero, and where the slow, deliberate dance of atoms and molecules sets the stage for the birth of stars. Unlike the diffuse expanses of interstellar gas, molecular clouds are dense enough that gravity begins to dominate the behavior of matter, pulling atoms together, fostering collisions and allowing complex chemistry to take hold. In these clouds, cold is not a mere backdrop. It is an active agent, regulating motion, stabilizing matter, and preserving the fragile balance necessary for the processes that will eventually ignite nuclear fusion and create new stars. Molecular clouds are composed primarily of hydrogen molecules, the simplest and most abundant form of matter in the universe, with smaller contributions from helium, carbon monoxide, water, ammonia, and other complex molecules. Within these clouds, hydrogen exists predominantly in its molecular form, H2, which only forms at low temperatures where collisions are slow and atoms can bond without being immediately disrupted by heat. The temperature of these clouds can range from about 10 Kelvin in the densest regions to 20 or 30 Kelvin in slightly warmer areas, still far colder than anything we encounter on Earth. At these extremes, molecular motion is sluggish, collisions are infrequent, and chemical reactions proceed at glacial speeds, allowing the slow accumulation of matter and the formation of structures that may endure for millions of years. These clouds are not uniform or static. Within a single molecular cloud, one can find filaments, clumps, and knots, structures shaped by turbulence, magnetic fields, and gravity. Cold plays a crucial role in this structuring. At higher temperatures, thermal pressure would resist compression, dispersing matter and preventing the accumulation necessary for star formation. But in the frigid environment of molecular clouds, thermal motion is subdued, allowing gravity to dominate. This delicate balance between motion and stasis, between energy and inertia, determines the rate at which clumps of matter collapse, the size and mass of emerging protostars, and the chemical complexity of the cloud itself. Temperature in this context is not merely a measure, it is a regulator of cosmic evolution, setting the conditions under which matter can organize itself over vast scales of space and time. The extreme cold within molecular clouds also facilitates chemistry that would be impossible at higher temperatures. Atoms and molecules stick to tiny dust grains, forming icy mantles where further reactions can occur. Hydrogen combines with oxygen to form water ice. Carbon interacts with hydrogen to form hydrocarbons, and nitrogen participates in forming ammonia and other nitrogen-bearing molecules. Over millions of years, these reactions accumulate, creating reservoirs of complex molecules that may eventually be incorporated into forming stars and planets. Cold, in this sense, is a preserver and enabler, slowing destructive reactions while allowing subtle, constructive processes to take place. It is the environment in which molecular diversity can flourish, setting the stage for the chemical richness that may one day seed life elsewhere. Observing molecular clouds is a challenge, in part because of their extreme cold and in part because of their opacity. Dense regions absorb visible light, rendering them nearly invisible against the backdrop of stars. To study them, astronomers rely on radio, microwave, and infrared wavelengths, detecting the faint emission of molecules and the subtle absorption of background radiation. These observations reveal not only the chemical composition and temperature of the clouds, but also their density, structure, and motion. By mapping these properties, scientists can infer the processes at work within the coldest regions, from turbulence to gravitational collapse, from chemical evolution to the eventual formation of protostars. Cold, in this context, is both a condition to be measured and a phenomenon that shapes the observational signature of the universe, providing insight into the mechanisms of star and planet formation. Even in these frigid environments, molecular clouds are dynamic. Turbulence creates filaments and knots, while magnetic fields thread through the gas, guiding motion and influencing collapse. Shocks from nearby supernovae, stellar winds, and radiation from young stars introduce localized heating, triggering chemical reactions, compressing gas, and even dispersing material. Yet despite these perturbations, the dominant condition remains one of extreme cold. Temperature regulates the pace of these processes, ensuring that matter accumulates slowly, that chemistry proceeds gradually, and that the cloud maintains coherence over timescales of millions of years. Without cold, molecular clouds could not serve as nurseries for stars. Without this frigid stability, the intricate dance of matter that leads to the formation of solar systems could not occur. The scale of molecular clouds is staggering. Some span dozens of light years, containing thousands or even hundreds of thousands of solar masses of gas and dust. Within these clouds, regions dense enough to form stars may occupy only a small fraction of the volume, yet the cold pervades all areas, maintaining stability, preserving chemical complexity, and ensuring that gravity can act unopposed in these key regions. Temperature gradients exist, with slightly warmer pockets near forming stars or regions of compression, yet the overall environment remains incredibly cold, a pervasive influence that shapes every process within the cloud. The relationship between cold and density is also fundamental to understanding these stellar nurseries. As regions within the cloud become denser, gravitational forces pull matter inward, raising pressure and temperature slightly, but the surrounding extreme cold ensures that this heating does not disrupt the collapse. Molecules remain bound, dust grains continue to accumulate icy mantles, and chemical reactions proceed slowly. Over time, these processes lead to the formation of dense cores, the seeds of future stars. Cold, therefore, is not merely a background condition, it is an active facilitator of stellar creation, regulating motion, chemistry, and structure simultaneously. Cold also plays a role in determining the timescale of star formation. In molecular clouds, processes unfold over millions of years, a slow, deliberate evolution governed by the low temperatures that dominate these regions. Collapsing cores gradually accumulate mass. Molecular reactions proceed at a deliberate pace, and the eventual ignition of nuclear fusion occurs only after sufficient material has been gathered. The slow pace imposed by extreme cold allows for the careful organization of matter, the preservation of chemical complexity, and the emergence of conditions suitable for the birth of stars and, eventually, planets. Observationally, cold molecular clouds provide insight into the early stages of star formation. Using radio telescopes and infrared detectors, astronomers can map the distribution of molecules such as carbon monoxide, ammonia, and water, revealing the density, temperature, and motion within the cloud. These observations show that even in the coldest regions, matter is not static. Turbulence, rotation, and interactions with nearby stars influence the dynamics, while cold ensures that chemical reactions and structural evolution proceed slowly, preserving the conditions necessary for star formation. Temperature, therefore, is both a controlling factor and a key observable, linking physical conditions to the processes that shape stellar nurseries. The chemical richness of molecular clouds is remarkable. Complex organic molecules, including prebiotic compounds, have been detected within these frigid environments, preserved by the extreme cold and slow molecular motion. Ice-coated dust grains serve as sites for chemical reactions that would be impossible in warmer environments, allowing the gradual formation of increasingly complex structures. Cold, in this context, acts as a conservator, slowing destructive processes while facilitating the emergence of complexity. These molecules may eventually be incorporated into forming planets, providing the raw materials for chemistry that, under the right conditions, could lead to life. Even in the frigid expanse of molecular clouds, interactions with radiation and cosmic rays introduce subtle energy into the system. These inputs can trigger localized heating, ionization, or chemical reactions, adding complexity to the cloud's evolution. Yet the overarching influence of cold remains dominant, regulating the pace, preserving structure, and maintaining the conditions necessary for the gradual accumulation of matter. Cold is both a stabilizing force and a shaping factor, ensuring that the processes within molecular clouds unfold with the precision required for star formation. The scale, temperature, and complexity of molecular clouds underscore the importance of cold in cosmic evolution. Without these frigid conditions, atoms and molecules would not accumulate. Chemical reactions would proceed too rapidly or be disrupted, and the slow, deliberate process of star formation could not occur. Cold is both the environment and the mechanism, providing stability, regulating chemistry, and allowing gravity to shape matter over millions of years. It is the silent force that governs the transformation of diffuse gas into the stars that light galaxies, the planets that orbit them, and the conditions that ultimately allow life to emerge. Even as we consider molecular clouds from our distant vantage point, the role of cold is evident. It preserves, it stabilizes, it enables. From the motion of individual molecules to the collapse of dense cores, from the slow accumulation of chemical complexity to the ignition of fusion in protostars, cold is the guiding principle, the invisible hand, and the patient architect of stellar nurseries. By studying these regions, scientists gain insight into the processes that have shaped the universe for billions of years, understanding how temperature, motion, and chemistry interact in the most extreme and fundamental ways. Molecular clouds demonstrate that cold is not absence, nor is it mere measurement. It is an active, essential property of the universe, shaping matter, guiding evolution, and enabling processes that unfold over immense distances and timescales. From the icy dust grains to the vast filaments stretching across light years, from the slow collapse of dense cores to the ignition of stars, cold is everywhere, orchestrating the emergence of structure, chemistry, and energy. In these frigid regions, the universe moves slowly, deliberately, and with precision, creating the foundations for the celestial landscapes we observe today, and providing a glimpse of the conditions under which all matter and energy organize themselves. Amid the sprawling filaments and dense regions of molecular clouds, there exist even smaller, more concentrated pockets of cold and darkness known as Bok globules. Named after the Dutch-American astronomer Bart Bok, who first studied these mysterious formations in the mid-20th century, these globules are tiny, isolated islands of extreme chill, drifting quietly in the vast interstellar medium. Despite their modest size, often just a fraction of a light year across, Bok globules play an outsized role in the cosmic story, serving as incubators for the birth of stars, laboratories for chemistry under near absolute zero conditions, and silent witnesses to the forces that shape galaxies. They are profound in their simplicity, cold, dense, dark, and extraordinarily efficient at preserving the delicate balance necessary for the slow processes of stellar formation. Bok globules are primarily composed of molecular hydrogen, with traces of helium, carbon monoxide, water ice, and a variety of complex molecules. Their interiors are extremely cold, typically ranging from 7 to 20 Kelvin, which is only a few degrees above absolute zero. At such low temperatures, atomic and molecular motion slows dramatically, collisions become infrequent, and chemical reactions proceed at glacial speeds. This extreme cold allows molecules to freeze onto tiny dust grains, forming icy mantles where further chemical interactions can occur over millions of years. In this sense, Bok globules are not inert or lifeless. They are dynamic systems in slow motion, their processes unfolding on timescales that dwarf human perception. Cold governs every aspect of their behavior, from structural stability to chemical evolution, ensuring that matter within these globules is organized, preserved, and prepared for eventual transformation. What makes Bok globules particularly fascinating is their isolation. Unlike larger molecular clouds, which may be influenced by nearby stars, radiation fields, or shock waves from supernova, these tiny globules are often sheltered from external disruptions. Their compactness and density shield the interior from ultraviolet radiation and stellar winds, creating a sanctuary where molecules can survive for millions of years without being destroyed or dispersed. The very nature of cold is amplified in these regions. Low thermal energy prevents expansion, suppresses motion, and maintains the integrity of the globule over extended periods. In this protective environment, atoms and molecules are free to interact at the slow, deliberate pace dictated by the frigid temperatures, allowing complex chemistry to unfold and laying the groundwork for the eventual emergence of protostars. Observing Bok globules is a challenge, because their extreme density and darkness render them nearly invisible in ordinary optical light. Instead, astronomers rely on infrared, microwave, and radio wavelengths. detecting the faint emission of molecules and the subtle absorption of background starlight. These observations reveal the shape, density and motion of the globules, as well as their chemical composition and thermal properties. Even with advanced instruments, it is remarkable that such small cold structures can be detected at distances of hundreds or thousands of light years. Each photon captured is a messenger from a region so cold and remote that its properties challenge human intuition, yet it conveys vital information about the fundamental processes governing star formation and molecular evolution. The cold within Bok globules also dictates the rate of chemical reactions. At just a few degrees above absolute zero, molecules move so slowly that collisions are rare, yet over millions of years, these rare interactions accumulate. Hydrogen combines with oxygen to form water, carbon combines with hydrogen to form simple hydrocarbons, and nitrogen participates in forming ammonia and other nitrogen-bearing compounds. Dust grains, coated with icy mantles, provide sites for additional reactions, allowing molecular complexity to emerge in an environment of extreme stasis. Cold, therefore, is not a barrier, but a facilitator. It slows processes to a pace compatible with the stability of the globule, while enabling the gradual accumulation of chemical richness that may one day become part of a newly forming star or planetary system. Even within these tiny, isolated regions, gravity slowly asserts its influence. Dense pockets within the globule gradually contract, drawing matter inward and increasing the local density. Cold ensures that thermal pressure does not counteract this collapse, allowing gravitational forces to dominate. Over hundreds of thousands or even millions of years, these dense regions can reach the critical threshold needed for nuclear fusion to ignite, giving birth to a new star. The process is deliberate, patient, and extraordinarily dependent on the frigid conditions maintained by the globule. Cold is both the enabler and regulator of stellar formation within these compact, dark pockets of space. The interplay of cold, gravity, and chemistry in Bok globules highlights the delicate balance required for the emergence of stars. Without the low temperatures, molecular motion would be too energetic, collisions too frequent, and chemical complexity too easily disrupted. Without cold, gravitational collapse would be opposed by thermal pressure, preventing the accumulation of sufficient mass for protostars to form. Cold acts as a stabilizing agent, maintaining the structural integrity of the globule and preserving the slow pace necessary for the interplay of physics and chemistry to unfold. It is a quiet but decisive force, shaping the very beginnings of stellar evolution. Bok globules are often surrounded by diffuse gas and dust, which forms a kind of protective cocoon. This external material shields the interior from radiation and stellar winds, helping to preserve the extreme cold within. Even minor variations in temperature can influence the stability of the globule, the rate of chemical reactions, and the onset of gravitational collapse. In this way, the isolation and temperature of Bok globules work together to create ideal conditions for star formation, ensuring that the processes inside proceed with precision and consistency over vast timescales. Cold is not simply a background feature. It is an active participant in the creation of stars and the organization of matter. The study of Bok globules also reveals the importance of cold in understanding the larger structure of galaxies. These tiny, frigid pockets are scattered throughout the Milky Way and other galaxies, embedded within larger molecular clouds and galactic disks. Their distribution, density, and motion contribute to the overall dynamics of star formation across the galaxy. By studying the properties of these cold globules, scientists can infer the processes that shape stellar populations, the rate of star formation, and the chemical evolution of galaxies over billions of years. Cold, in this context, is both a local and a global factor, influencing matter on scales from a single light-year to the span of an entire galaxy. Even within the cold interiors of Bok globules, there are variations in density and temperature. Turbulence, rotation, and magnetic fields introduce subtle complexity. creating regions that are slightly warmer or cooler, denser or more diffuse. These variations are critical in determining where stars will form, how massive they will become, and what chemical composition they will inherit from the globule. Cold provides the overarching stability, while localized variations introduce the diversity and complexity necessary for star formation to proceed. Without this extreme chill, the careful interplay of forces, chemistry, and gravity would be disrupted, and the stellar nurseries would lose the precise conditions needed to give rise to new stars. Bock globules also illustrate the role of cold in the preservation of matter. Within their interiors, molecules that would be unstable or reactive at higher temperatures can survive for millions of years. Ice mantles on dust grains protect these molecules from radiation, while the slow motion of particles prevents destructive collisions. This preservation allows chemical complexity to accumulate, providing the raw materials for future planetary systems. Cold, therefore, is not just a facilitator of star formation, it is a conservator of molecular heritage, a slow, patient guardian of the building blocks that may one day contribute to life elsewhere in the universe. Even the smallest Bock globules, with masses comparable to a few suns, demonstrate the remarkable influence of cold. Their size, density, and temperature allow for the formation of low-mass stars, while larger globules can give rise to clusters of stars. The extreme cold ensures that molecular motion is minimized, thermal pressure is low, and chemical reactions proceed at a pace compatible with stability. Observations show that these globules are often elongated, filamentary, or irregular, shaped by turbulence, magnetic fields, and external radiation, yet their interiors remain remarkably cold and stable. Cold, in this sense, is both a constraint and an enabler, defining the conditions under which matter can transform into stars. Even as we reflect on the tiny scale of Bock globules relative to the galaxy, it becomes clear that their extreme cold has cosmic significance. These small dark pockets are the seeds of stellar creation, the sites where matter is organized, preserved, and prepared for the emergence of light. The frigid temperatures ensure stability, enable chemistry, and regulate gravitational collapse, creating conditions that are essential for the universe to produce stars, planets, and eventually the complex chemistry necessary for life. Cold, in these globules, is both a physical property and a guiding principle, shaping matter with patience, precision, and remarkable consistency. The study of Bock globules also provides a window into the interplay of scales in the universe. From the motion of individual molecules to the collapse of dense cores, from the preservation of chemical compounds to the ignition of nuclear fusion, cold operates across vast ranges, linking the microscopic to the macroscopic. These tiny, isolated pockets, seemingly insignificant against the backdrop of galaxies, demonstrate that extreme temperature is a fundamental factor in cosmic evolution. Without the persistent chill of Bock globules, the universe would be unable to organize matter into stars, and the intricate structures we observe across galaxies would not exist. In contemplating these tiny islands of extreme chill, we begin to see cold not merely as an absence of heat, but as a force that structures, preserves, and enables. The balance of temperature, density, and chemical potential within Bock globules dictates the rate of star formation, the accumulation of molecular complexity, and the emergence of structure from the otherwise diffuse interstellar medium. Cold is the silent sculptor, the patient regulator, and the essential condition that allows the universe to transform gas and dust into the stars and planets that will light galaxies for billions of years. Even as our imagination drifts beyond these globules, into the larger molecular clouds, into the icy voids between stars, and into the faint radiation of the cosmic microwave background, the role of cold remains central. It is the defining characteristic of stellar nurseries, the preservative of chemical heritage, the facilitator of gravitational collapse, and the regulator of cosmic evolution. From the smallest Bock globule to the largest galaxy, cold structures matter, shapes chemistry, and orchestrates the slow, deliberate processes that give rise to light, structure, and the potential for life. Far beyond the familiar chill of Bok globules, even deeper into the interstellar expanse, there exists a place where cold reaches its most extreme expression, a region of space so frigid that it defies intuitive understanding and challenges the very limits of physics. This is the Boomerang Nebula, often called the coldest known place in the universe. Located roughly 5,000 light-years away in the constellation Centaurus, it is a ghostly cloud of gas and dust expanding outward from a dying star, a frozen whisper in the cosmic darkness, holding temperatures lower than even the cosmic microwave background. At just 1 degree Kelvin above absolute zero, the Boomerang Nebula is colder than any laboratory on Earth has ever achieved until recent decades, and it serves as a striking example of the extremes that nature can reach when energy disperses across unimaginable distances. The nebula earns its chilling title because of the unique dynamics of its expanding gas. Unlike regions of space heated by starlight, shock waves, or cosmic radiation, the Boomerang Nebula's matter is moving outward at incredibly high speeds, rapidly dispersing into surrounding space. This expansion causes the gas to cool in a process known as adiabatic cooling. Essentially, as the gas spreads out, its molecules lose kinetic energy, slowing down, and the temperature drops. It is a natural refrigerator on a cosmic scale, where motion itself drives the frigid conditions. The nebula's temperature is astonishingly low, reaching just 1 degree Kelvin, a fraction below the cosmic microwave background, demonstrating that cold can exist not only as a baseline set by radiation, but as a product of motion and expansion in space. The Boomerang Nebula is also remarkable because it challenges our sense of scale and perception. Measuring roughly 0.9 light-years across, it is relatively small by cosmic standards, yet its low temperature and rapid expansion make it one of the most extreme environments in the universe. Within this nebula, molecular hydrogen and dust grains move at glacial speeds, and chemical reactions occur extraordinarily slowly, if at all. This extreme cold is not merely a curiosity. It provides scientists with a natural laboratory to study the behaviour of matter near absolute zero, the limits of molecular motion, and the interaction of energy, gravity, and expansion in a rarefied environment. Observing and measuring these properties requires precision instruments capable of detecting faint emissions in the microwave and submillimeter range, translating the subtle signals of molecular motion into a picture of temperature, density, and dynamics. The star at the heart of the Boomerang Nebula plays a crucial role in creating this frozen environment. It is a dying star, shedding its outer layers into space in the form of a stellar wind. As these layers expand, they cool dramatically, dropping to temperatures colder than anything in the surrounding interstellar medium. This process contrasts sharply with the warmth typically associated with stars, which radiate energy and heat their surroundings. In the Boomerang Nebula, the motion of matter dominates over radiant heating, illustrating how cold can be generated not by the absence of energy, but by the redistribution of it. The nebula demonstrates that temperature in space is not merely a measure of proximity to a heat source, but a function of dynamics, density, and energy flow. Observing the Boomerang Nebula also highlights the interplay between cold and chemical complexity. At such low temperatures, molecules can persist for extremely long periods, without being destroyed by radiation or collisions. Dust grains coated in icy mantles provide sites for further reactions, preserving chemical compounds that may one day be incorporated into newly forming stars or planetary systems. In this way, the nebula serves not only as a record of extreme physical conditions, but also as a potential incubator for molecular structures, a cold reservoir of material that may contribute to future cosmic evolution. The extreme chill slows motion, preserves matter, and allows the delicate processes of chemistry and aggregation to unfold in a manner that is virtually imperceptible on human timescales. Measuring the temperature of the Boomerang Nebula presents its own challenges. At a mere 1 degree above absolute zero, standard observational techniques are insufficient. Astronomers rely on submillimeter and radio observations, analysing the emission lines of molecules like carbon monoxide and hydrogen to infer the kinetic energy of particles and the overall temperature of the gas. These measurements reveal not only the extreme cold, but also the velocity and structure of the expanding material, offering insight into the processes that drive this extraordinary cooling. The precision required to measure such low temperatures underscores both the fragility of the signals and the sophistication of modern observational astronomy. The Boomerang Nebula also serves as a reminder of the diversity of conditions in the universe. While other regions of space, such as the cosmic microwave background or molecular clouds, provide cold environments, none achieve the combination of expansion, density, and extreme temperature found here. The nebula illustrates that cold is not uniform across space. It is shaped by local dynamics, motion, and structure. Expansion, rather than simply distance from a star or the presence of radiation, can produce temperatures that push the limits of what is physically achievable, demonstrating that cold is an active, dynamic force in the universe. Within the nebula, the behaviour of particles is extraordinary. At 1 degree Kelvin, molecular motion is almost negligible. Collisions are infrequent and energy transfer is minimal. This near stasis creates an environment where matter is preserved in its simplest forms, maintaining chemical and structural integrity over vast timescales. In such an environment, reactions proceed only when catalyzed by specific conditions, meaning that the nebula acts as both a laboratory and a preservative, holding matter in a frozen pause, ready to participate in future cosmic events once conditions change. Cold, in this sense, is both protective and regulatory, shaping the destiny of matter in subtle but profound ways. The Boomerang Nebula also emphasizes the scale of time in relation to cold. Processes that would unfold in seconds on Earth can take thousands, millions, or even billions of years in such an environment. Expansion proceeds gradually, chemical interactions accumulate slowly, and the structure of the nebula persists over immense spans. The extreme cold ensures that change is deliberate, measured, and preserved, highlighting the role of temperature not merely as a static property, but as a determinant of pace, stability, and evolution. Cold dictates the rhythm of matter, guiding its transformations across time and space in ways that are almost imperceptible, but fundamentally crucial to the evolution of the cosmos. Even the light escaping from the Boomerang Nebula is affected by the extreme cold. Emissions from molecules are faint, stretched across long wavelengths, and require careful detection to reveal the properties of the nebula. Observing these signals provides insight into not only the temperature, but also the motion, density, and chemical composition of the cloud. The faint glow of radiation against the darkness of space underscores the duality of cold. It preserves, slows, and stabilizes matter, yet also enables subtle signals that allow us to measure and understand the processes occurring within. Cold is both a constraint and a conduit, simultaneously quieting activity and conveying information. The Boomerang Nebula also provides context for understanding cold elsewhere in the universe. While molecular clouds, Bok globules, and interstellar space are extremely cold, the nebula demonstrates that specific dynamics can produce even more extreme conditions. Expansion-driven cooling, isolation from heating sources, and the redistribution of matter combine to create a region colder than the cosmic microwave background, colder than almost anything else observed in space. This highlights the diversity of mechanisms by which the universe achieves cold and the importance of extreme temperature in regulating the evolution of matter. Even for human understanding, the Boomerang Nebula challenges intuition. 1 degree Kelvin is virtually unimaginable, far colder than any natural environment on Earth. It stretches our concept of temperature beyond experience, forcing us to rely on instruments, observation, and careful inference. Yet in doing so, it also provides a remarkable lesson, that cold is not simply a measure of absence, but a condition that structures matter, preserves chemistry, and guides cosmic evolution. It is active, pervasive, and essential, shaping processes on scales both microscopic and galactic. The nebula's extreme cold also affects the potential for chemistry and complexity within its boundaries. Molecules that might rapidly dissociate in warmer regions can survive for extended periods, slowly interacting, adhering to dust grains, and forming the foundations for more complex chemical structures. These processes, though slow and subtle, are essential for the eventual seeding of star systems with the raw materials necessary for planets and potentially life. Cold is both a conservator and a facilitator, providing a stable, extreme environment in which matter can endure and evolve. Even in its isolation, the Boomerang Nebula interacts with the surrounding interstellar medium. Radiation from distant stars, cosmic rays, and faint background energy introduce minor perturbations, yet the dominant condition remains extreme cold. This persistence highlights the power of temperature to govern processes, maintain stability, and preserve structure. Cold is not passive. It is a defining characteristic, a regulator, and a force that dictates the behavior of matter over immense spans of space and time. By studying the Boomerang Nebula, scientists gain insight into the extremes of temperature, the limits of molecular motion, and the influence of expansion on thermal conditions. The nebula provides a rare natural laboratory, a place where we can observe matter at temperatures approaching the theoretical minimum, where motion is subdued, chemistry proceeds slowly, and the laws of physics operate under conditions far removed from everyday experience. Cold, in this context, is a measure of both physical state and cosmic significance, a key parameter in understanding the evolution of matter and energy. Even as our minds attempt to grasp its magnitude, the Boomerang Nebula illustrates the relationship between cold, motion, and time. Expansion drives cooling, molecules slow, and matter is preserved over vast timescales. Chemical reactions occur with extraordinary deliberation, and gravity slowly shapes matter, setting the stage for the eventual emergence of new stars. Extreme cold is the orchestrator of these processes, the invisible hand that ensures matter behaves predictably, consistently, and in accordance with the laws of physics. The Boomerang Nebula, with its ghostly shape and record-setting temperature, reminds us that cold is not merely a sensation or a number. It is a force that organizes, stabilizes, and enables. It is the patient sculptor of matter, the regulator of chemistry, and the foundation for processes that unfold over millions and billions of years. From the faint motions of molecules to the grand scale of nebular expansion, cold dictates the rhythm of cosmic evolution, creating conditions that are both extreme and essential. Exploring the coldest regions of the universe, from molecular clouds to the Boomerang Nebula, raises a question that is as fascinating as it is essential. How do we know the temperatures of places so distant, dark, and extreme that no human could ever feel them directly? Measuring cosmic temperatures is not a matter of touching, tasting, or even seeing in the traditional sense. It is a precise science that relies on understanding the behavior of matter and radiation, interpreting faint signals that traverse thousands or millions of light years, and translating these signals into temperatures that challenge human comprehension. To grasp the enormity of these measurements, we must first consider the subtle ways in which temperature manifests in space, and how those manifestations are captured by human ingenuity. Temperature, at its most fundamental level, reflects the kinetic energy of particles. The faster they move, the warmer the substance; the slower they move, the colder it becomes. In interstellar space, where gas and dust are sparse and collisions infrequent, particle motion is extraordinarily slow. Measuring the kinetic energy of such particles is not straightforward, because they are separated by vast distances and their energy is tiny compared to familiar conditions on Earth. Scientists rely on indirect methods, observing the interaction of matter with the electromagnetic radiation. Molecules emit or absorb photons at characteristic frequencies, and the intensity and distribution of this radiation depend on the temperature and density of the material. By carefully analysing these emissions, researchers can infer the thermal state of a region, even when direct contact is impossible. One of the primary tools for measuring cosmic temperatures is spectroscopy. Molecules and atoms have discrete energy levels, and transitions between these levels produce or absorb light at specific wavelengths. In cold regions, such as molecular clouds or Bok globules, these transitions occur predominantly in the microwave and infrared portions of the electromagnetic spectrum. By measuring the intensity and profile of these spectral lines, astronomers can determine the velocity, density, and temperature of the gas. For example, carbon monoxide, a common tracer molecule, emits radiation that can reveal not only its motion, but also the kinetic temperature of the surrounding hydrogen gas. The faintness of these emissions requires highly sensitive instruments and careful calibration, often mounted on satellites or high-altitude observatories to minimize interference from Earth's atmosphere. In addition to molecular emissions, continuum radiation provides another window into temperature. Dust grains within clouds absorb and re-radiate energy in the infrared, creating a faint glow that is indicative of the surrounding temperature. By analysing this emission, scientists can estimate the thermal state of dust and gas, revealing regions that are warmer or colder within the same cloud. The combination of spectral lines and continuum measurements allows for a comprehensive picture of temperature distribution, density, and chemical composition. In this way, the universe itself provides the tools for understanding its own thermal properties, with cold acting both as a constraint and a signal. Measuring the extreme cold of places like the Boomerang Nebula presents additional challenges. Temperatures of just 1 degree above absolute zero produce emissions that are exceptionally weak, requiring observations at sub-millimeter wavelengths. Telescopes such as ULMA, operating in these ranges, detect the faint vibrations of molecules and dust, providing precise measurements of both motion and temperature. By modelling the dynamics of expanding gas and the radiative transfer of energy, astronomers can calculate the temperature with remarkable accuracy. The Boomerang Nebula, therefore, is not only an extreme environment, it is a natural laboratory where human instruments translate nearly imperceptible signals into an understanding of matter at the limits of cold. Laboratory experiments on Earth complement these observations. Scientists use cryogenic techniques to reproduce temperatures approaching those of molecular clouds and nebulae. By cooling gases, liquids, or solid surfaces to fractions of a degree above absolute zero, researchers can study molecular motion, chemical reactions, and quantum effects under extreme cold. These experiments provide insight into the behavior of matter in conditions analogous to those in space, allowing us to interpret astronomical data more accurately. The connection between laboratory research and cosmic observation underscores the universality of physical laws. The same principles governing atoms in a refrigerator on Earth apply to the Boomerang Nebula, Bok globules, and interstellar clouds. Radiative transfer models are another essential tool. By considering how energy moves through matter, how photons are absorbed, scattered, or emitted, scientists can estimate temperature distributions even when direct measurements are impossible. These models require detailed knowledge of molecular properties, densities, and interactions with radiation. When combined with observational data, they allow researchers to construct three-dimensional maps of temperature, density, and composition, revealing the intricate structure of cold regions in space. Cold is therefore both the subject of study and a parameter within the models, shaping predictions and guiding interpretation. Even the cosmic microwave background, the faint afterglow of the Big Bang, is measured through similar principles. Sensitive instruments on satellites like Planck detect minute fluctuations in microwave radiation across the sky, translating variations of just a few microkelvin into maps of density, temperature and motion from the early universe. These measurements reveal the seeds of galaxies, the imprint of gravity, and the distribution of matter on the largest scales. Cold in this context becomes a window into history, a signal that preserves the conditions of the universe at its earliest moments. By understanding the CMB, we gain insight not only into extreme temperature, but also into the evolution of cosmic structure over billions of years. Beyond observation, theoretical calculations provide essential checks on our understanding of cold. Physics predicts the behavior of matter at low temperatures, the emission spectra of molecules, and the effects of expansion on gas. These predictions can be compared to measurements, validating models or revealing discrepancies that hint at new phenomena. In the case of the Boomerang Nebula, theory predicts that rapid expansion should cool gas below the cosmic microwave background, and observations confirm this extraordinary chill. Cold, therefore, is both measurable and predictable, constrained by the laws of physics yet capable of producing phenomena that challenge our imagination. Another method for measuring cosmic temperatures involves analysing molecular motion directly. Spectral line widths, for instance, reflect the velocity distribution of particles, which is closely related to temperature. Broader lines indicate faster motion and higher temperatures, while narrow lines suggest slower movement and extreme cold. By studying these line widths in molecular clouds or Bok globules, scientists can quantify the kinetic energy of particles and derive precise temperature estimates. Even at temperatures near absolute zero, these measurements reveal subtle motions that are essential for understanding cloud dynamics, chemical reactions, and star formation. Cold also influences the design and operation of instruments. To measure temperatures lower than the cosmic background, detectors themselves must be cooled, often to millikelvin temperatures. Cryogenic systems using liquid helium, dilution refrigerators, or advanced superconducting technologies allow instruments to detect faint emissions without interference from their own thermal energy. In this way, the pursuit of extreme cold in cosmic observation drives innovation, requiring not only understanding but also engineering that mirrors the conditions being studied. The interplay between observation and technology highlights how cold is both a natural phenomenon and a challenge for human ingenuity. Even seemingly simple measures, like the brightness of a star or the infrared glow of dust, depend on temperature. Hotter stars emit more visible light, while cooler dust radiates primarily in the far infrared. By modelling these emissions, astronomers can infer the temperature of objects across vast distances, revealing cold regions hidden in darkness, preserved against radiation, and shaped by motion and density. Cold is thus encoded in light, providing the raw material for understanding the thermal state of the universe. In addition, cold interacts with chemical complexity. Molecules in frigid environments respond differently than in warmer regions, producing spectral signatures unique to low-temperature conditions. Detecting these molecules allows scientists to map temperature distributions, infer the presence of icy mantles, and understand the slow evolution of chemistry in star-forming regions. Cold, in this sense, is both the environment and the signal, governing processes while enabling observation. By combining observational data, laboratory experiments, theoretical models, and instrument design, scientists can measure and understand the temperatures of the coldest places in the universe. From molecular clouds to Bok globules, from the Boomerang Nebula to intergalactic space, temperature is revealed through subtle motions, faint emissions, and careful interpretation. Cold is never abstract. It is quantifiable, measurable, and central to understanding cosmic evolution. Even as we reflect on these techniques, it becomes clear that measuring cosmic temperatures is a blend of ingenuity, patience, and understanding. It requires translating faint distant signals into a physical quantity that can be compared, modelled, and understood. Cold, in this context, is both the subject of study and a guide, shaping the methods we use to explore the universe and revealing the delicate interplay of motion, energy, and structure in extreme environments. The universe itself is a laboratory. The tools are light and radiation, and temperature is both a measure and a condition that governs the behaviour of matter on scales both vast and microscopic. By studying the coldest regions of space, we gain not only a sense of the limits of temperature, but also insight into the processes that structure galaxies, form stars, and preserve matter. Cold is a guiding principle, dictating motion, stabilizing matter, and regulating the pace of chemical reactions. Measuring it requires understanding physics, interpreting signals, and designing instruments capable of detecting subtle traces across unimaginable distances. The extreme chill of the universe, from molecular clouds to the Boomerang Nebula, is a record of both energy and history, and measuring it is a way to connect human understanding with the cosmos itself. While the coldest regions of the universe stretch across unimaginable distances, far beyond what any human could ever visit, we have found ways to recreate aspects of these extremes here on Earth. Cryogenic laboratories allow us to simulate temperatures approaching those of molecular clouds, globules, and even the Boomerang Nebula, providing a tangible connection to the frigid conditions that govern the formation of stars, the evolution of molecules, and the behaviour of matter in ways that our everyday experience cannot grasp. These experiments are as much about patience and precision as they are about technology, requiring meticulous control, sophisticated equipment, and a deep understanding of physics to achieve conditions just fractions of a degree above absolute zero. Cryogenics, the science of extreme cold, relies on a combination of cooling techniques. Liquid helium, for instance, has been used for decades to reach temperatures of just a few Kelvin, allowing researchers to study matter in conditions similar to those found in interstellar space. Helium-4 and helium-3 isotopes have unique properties at low temperatures, including superfluidity, which enable cooling to extraordinarily low levels. More advanced techniques, such as dilution refrigeration, have pushed temperatures even closer to absolute zero, reaching millikelvin ranges where quantum effects dominate and atoms behave in ways that are entirely foreign to our everyday intuition. In these conditions, molecules slow almost to a standstill, chemical reactions occur at glacial rates, and matter can enter exotic states that reveal the underlying principles of physics. The purpose of simulating cosmic cold on Earth is multifaceted. One goal is to understand the behaviour of matter under extreme conditions. In molecular clouds, atoms and molecules move sluggishly, collisions are rare, and reactions occur over timescales that span millions of years. In the laboratory, cryogenic experiments allow scientists to replicate these conditions in miniature, studying how hydrogen molecules interact with dust grains, how complex molecules form, and how quantum effects influence behaviour at low temperatures. These insights help interpret astronomical observations, providing context for the faint emissions detected from the Boomerang Nebula, globules, and other frigid regions. Cold is no longer abstract. It becomes measurable, manipulable, and understandable. Cryogenic experiments also allow for the study of exotic states of matter that only emerge at extremely low temperatures. Superfluids, for example, flow without viscosity, defying classical expectations and illustrating the unique behaviour of matter near absolute zero. Bose-Einstein condensates, formed when a collection of atoms is cooled to near-zero temperatures, act as a single quantum entity, displaying interference patterns and coherence on macroscopic scales. These states provide a direct glimpse into the strange and subtle physics that dominate the coldest environments, where conventional notions of heat, motion, and energy are pushed to their limits. Studying these conditions on Earth informs our understanding of space, revealing how extreme cold can influence both microscopic and macroscopic processes. One fascinating aspect of cryogenic research is how it mirrors the conditions of the universe on vastly different scales. In molecular clouds and Bok globules, low temperatures slow atomic and molecular motion, preserve chemical complexity, and enable the gradual accumulation of matter into dense cores that eventually form stars. In laboratories, similar effects are observed on a tiny scale. Atoms move sluggishly, reactions proceed slowly, and exotic quantum behaviors emerge. By connecting these scales, scientists bridge the gap between the human and the cosmic, using extreme cold as a common thread that links laboratory physics to interstellar processes. Cold, in this sense, is both universal and instructive, guiding our understanding across space and time. Cryogenic facilities also allow the study of materials under conditions that reveal their fundamental properties. Metals, superconductors, and insulators behave differently at temperatures approaching absolute zero. Thermal conductivity changes, electrical resistance drops, and quantum effects dominate. These studies not only provide insight into fundamental physics, but also have practical applications, informing the design of detectors, telescopes, and instruments used to measure cosmic temperatures. Instruments intended to study molecular clouds or the Boomerang Nebula must themselves operate in extreme cold to minimize noise and interference. Cryogenics allows us to replicate these conditions, ensuring that the delicate signals from space can be captured and interpreted accurately. Even the chemical behavior of simple molecules is transformed at cryogenic temperatures. Reactions that would occur rapidly at room temperature slow dramatically, allowing scientists to isolate intermediate products and study reaction pathways in unprecedented detail. Hydrogen, carbon monoxide, and ammonia, common in molecular clouds, behave differently when cooled near absolute zero, adhering to surfaces, forming clusters, or entering exotic quantum states. These experiments provide context for the chemistry occurring in cold regions of space, revealing how complex molecules can survive, accumulate, and participate in the processes that lead to star formation. Cold is both a laboratory tool and a natural condition, illustrating the universality of physical laws. The challenge of achieving and maintaining extreme cold on Earth is formidable. Cryogenic systems must be meticulously insulated, shielded from heat leaks, and carefully controlled to prevent temperature fluctuations. Even minute vibrations or thermal radiation can disrupt the delicate balance required to reach millikelvin ranges. Yet, when these conditions are achieved, the results are extraordinary. Researchers can observe matter behaving in ways that are entirely inaccessible at higher temperatures, revealing phenomena that mirror the slow, deliberate processes occurring in the Boomerang Nebula or Bok globules. Cold becomes a lens through which we can study the universe in miniature, gaining insight into processes that unfold over millions of years and across light years of space. Cryogenic experiments also reveal the relationship between cold and time. At low temperatures, reactions slow, molecular motion diminishes, and changes occur over extended periods, providing a direct analogy to the slow evolution of interstellar clouds. By observing these processes in the laboratory, scientists can extrapolate to cosmic timescales, understanding how cold regulates the pace of star formation, the accumulation of chemical complexity, and the preservation of matter. Extreme cold acts as both regulator and preserver, ensuring that processes unfold with precision and stability, whether in a tiny lab apparatus or a nebula thousands of light years away. Even in laboratories, the interplay of cold and structure is evident. Dust analogues, icy surfaces, and simulated interstellar molecules behave differently under frigid conditions, revealing insights into aggregation, adhesion, and chemical interaction. Molecules freeze onto surfaces, form clusters, and slowly react over extended periods. These observations provide a window into the processes that occur within Bok globules, molecular clouds, and other cold regions of space, connecting controlled experiments on Earth to the natural phenomena that shape galaxies and star systems. Cold, in this sense, is both a condition and an experiment, a parameter that defines behavior while allowing discovery. Cryogenic studies also inform our understanding of the limits of cold. Absolute zero, the point at which all classical motion ceases, remains unattainable, but laboratory experiments approach it closely, revealing the influence of quantum mechanics, zero-point energy, and the persistence of motion even at the lowest temperatures. Observing matter under these conditions allows scientists to test fundamental theories of physics, understand the behavior of atoms and molecules, and refine models that are applied to cosmic environments. Cold, therefore, is not only a phenomenon to be measured, but also a tool for expanding human knowledge, bridging the gap between observation, theory, and experimental verification. In addition, cryogenic experiments highlight the importance of isolation and stability. Just as Bock globules are shielded from external radiation to preserve their cold interiors, laboratory systems require shielding from heat, electromagnetic interference, and vibrations. Maintaining stability allows the extreme conditions to persist long enough for meaningful measurements and observations. Cold in this context is both fragile and powerful, demanding careful control while enabling profound insights into the behavior of matter under the most extreme conditions imaginable. Even the smallest cryogenic setups reveal the universality of cold in shaping matter. At millikelvin temperatures, atoms exhibit collective behaviors, form condensates, and reveal quantum effects that are not apparent at higher temperatures. These behaviors mirror, on a microscopic scale, the slow-motion chemistry and physics occurring in molecular clouds, Bock globules, and nebulae. Cold acts as a bridge between human-scale experiments and cosmic phenomena, demonstrating that the principles governing temperature, motion, and energy are consistent across scales, from laboratory apparatus to interstellar expanses. Cryogenic research also underscores the patience required to study extreme cold. Processes unfold slowly, measurements must be repeated, instruments calibrated, and environmental conditions meticulously maintained. This mirrors the universe itself, where cold regions such as the Boomerang Nebula or molecular clouds evolve over millions of years, preserving chemical complexity, regulating motion, and facilitating star formation. Cold is both slow and precise, a governing principle that structures matter, controls reactions, and ensures the stability necessary for evolution, whether in space or in the laboratory. Ultimately, cryogenic laboratories provide a tangible connection to the coldest regions of the universe. They allow us to simulate, observe, and understand temperatures approaching absolute zero, providing insight into molecular motion, chemical reactions, exotic states of matter, and the principles that govern cosmic evolution. Cold, in these experiments, is both the subject and the tool, a condition that enables discovery, preserves structure, and links human understanding to the vast frigid reaches of interstellar space. By recreating the extreme chill of the cosmos on Earth, scientists can study processes that would otherwise be inaccessible, from the behavior of molecules in molecular clouds to the dynamics of dust in Bock globules, from the preservation of matter in the Boomerang Nebula to the subtle quantum effects that emerge near absolute zero. Cold becomes a laboratory itself, a means of bridging scales, testing theories, and understanding the universe in both detail and grandeur. It is a reminder that even in the most extreme conditions, matter follows predictable laws, that temperature governs behavior, and that the slow, deliberate processes of the cosmos can be studied, measured, and understood here on our small, warm planet. As we move from the simulated cold of Earth's laboratories toward the conceptual extremes of the universe, we encounter the ultimate boundary of temperature, absolute zero. This is the theoretical limit of cold, a point at which molecular motion ceases in classical physics, a place where energy, as we usually understand it, is minimized to its lowest possible state. Absolute zero, defined as 0 Kelvin, or minus 273.15 degrees Celsius, represents not only a physical benchmark, but also a fundamental principle that governs the behavior of matter, energy, and the evolution of systems throughout the cosmos. Understanding absolute zero is crucial for appreciating the extremes we encounter in interstellar clouds, Bok globules, and the Boomerang Nebula, and for contextualizing the extraordinary chill that defines the coldest places in the universe. Absolute zero is a conceptual frontier because it is unreachable in practice. No matter how efficiently we remove energy from a system, residual motion always persists due to quantum mechanical effects, known as zero-point energy. At the atomic and subatomic level, particles cannot be completely at rest, even in a perfectly isolated environment. This persistence of motion reflects the fundamental uncertainty inherent in the universe, a reminder that cold, even in its most extreme form, is never entirely absolute. It challenges our intuition, suggesting that temperature is not merely a measure of motion, but a complex interaction of energy, constraints, and quantum behavior. Cold, then, becomes a spectrum rather than a fixed point, stretching from the temperatures we experience on Earth to the theoretical minimum defined by the laws of physics. In laboratories on Earth, scientists have approached temperatures within billionths of a degree above absolute zero, using techniques such as laser cooling, magnetic trapping, and dilution refrigeration. At these temperatures, matter behaves in ways that are entirely foreign to our everyday experience. Atoms can condense into Bose-Einstein states, behaving as a single quantum entity, or exhibit superfluidity flowing without resistance. These behaviors reveal the delicate and counterintuitive physics that govern extreme cold, and they provide insight into the conditions that prevail in cosmic environments where temperatures approach the theoretical limit. In both cases, whether in the lab or in space, cold is a regulator, a stabilizer, and a facilitator of unique physical processes. Absolute zero also defines a boundary for thermodynamics. The third law of thermodynamics states that as a system approaches 0 Kelvin, its entropy, or degree of disorder, approaches a minimum. In practical terms, this means that systems become increasingly ordered as temperature decreases, and their behavior becomes more predictable. In the universe, regions approaching extreme cold, such as the Boomerang Nebula, demonstrate the principles of low entropy and energy minimization. Molecular motion slows, collisions become rare, and matter behaves in a remarkably stable manner. Cold is both a measure and a driver of order, shaping the behavior of matter in ways that are subtle yet profound. Even in space, absolute zero remains theoretical. The cosmic microwave background provides a universal floor of approximately 2.7 Kelvin, setting a baseline temperature for the majority of the universe. However, localized conditions, such as the rapid expansion of gas in the Boomerang Nebula, can temporarily achieve temperatures below this cosmic average, reaching near 1 Kelvin. These extremes illustrate that cold is not only defined by ambient radiation, but by dynamics, motion, and the interaction of matter with its environment. Temperature in this context becomes a tool for understanding both energy distribution and structural evolution in the cosmos. In the study of cold, absolute zero is also a guide for experimentation. Cryogenic laboratories aim to simulate conditions approaching this limit, allowing scientists to investigate molecular motion, quantum effects, and the behavior of matter under extreme conditions. These experiments reveal that as temperature decreases, classical intuitions about motion, pressure, and chemistry become insufficient. Quantum effects dominate, and the behavior of particles is governed by principles that are only apparent near the coldest attainable states. Observing these effects provides insight into the universe at both microscopic and cosmic scales, illustrating the universality of cold as a governing principle. Chemical behavior is particularly sensitive to extreme cold. In molecular clouds, temperatures approaching 10 Kelvin, slow reactions to rates that allow complex molecules to persist for millions of years. In the laboratory, approaching absolute zero similarly slows motion, and stabilizes compounds, allowing for detailed observation of reaction pathways and intermediates that would be fleeting at higher temperatures. Cold, in this sense, is not an absence but a facilitator, creating a controlled environment in which the underlying rules of matter can be observed, preserved, and understood. Absolute zero also has implications for energy and motion. In the classical sense, temperature reflects the average kinetic energy of particles. As temperature approaches zero, this energy diminishes, and motion becomes nearly negligible. However, quantum mechanics ensures that some residual motion, zero-point energy, remains. This residual motion is a fundamental aspect of the universe, reminding us that cold is not simply the cessation of activity, but a limit defined by the interplay of classical and quantum principles. Understanding this boundary informs both laboratory experiments and our interpretation of cold regions in space, providing a framework for measuring and conceptualizing the behavior of matter under extreme conditions. The pursuit of absolute zero has driven technological innovation. Superconductors, quantum computers, and precision measurement instruments all rely on extreme cooling techniques to achieve stable, low-temperature conditions. In space research, detectors must be cooled to millikelvin temperatures to accurately measure the faint radiation from molecular clouds, Bok globules, and the Boomerang Nebula. Cryogenic techniques are essential not only for creating extreme cold, but for observing it, allowing us to capture the subtle signals that reveal the temperature, composition, and motion of matter across the universe. Cold, in this context, is both a phenomenon and a challenge, demanding ingenuity and precision in measurement. Even theoretically, absolute zero defines a critical boundary for our understanding of the universe. It represents the point at which classical motion ceases, the minimum kinetic energy achievable, and a reference for interpreting the extreme cold observed in space. The proximity of cosmic regions, such as the Boomerang Nebula or dense molecular clouds, to this limit illustrates how nature exploits the principles of thermodynamics to produce environments conducive to star formation, chemical preservation, and structural stability. Cold, therefore, is a central parameter, governing both physical behavior and cosmic evolution. The slow pace of processes near absolute zero is also revealing. In the coldest molecular clouds, reactions unfold over millions of years. In the Boomerang Nebula, expansion-driven cooling preserves matter in a near-frozen state. In laboratories, reaching millikelvin temperatures slows molecular motion to the point where quantum phenomena dominate. Across these scales, cold dictates the rhythm of evolution, ensuring that change occurs deliberately, predictably, and in alignment with the physical laws that govern the universe. Temperature becomes a regulator of time as much as energy, controlling the rate of processes in both the cosmic and laboratory contexts. Absolute zero also provides perspective on the range of temperatures in the universe, from the warmth of a star to the icy peripheries of the solar system, from the faint hum of the cosmic microwave background to the 1 Kelvin chill of the Boomerang Nebula. The concept of absolute zero anchors our understanding. It allows us to interpret measurements, model chemical and physical behavior, and conceptualize the extremes of space. Cold is both relative and absolute, a spectrum defined by energy, motion, and fundamental physical limits. Even in our everyday experience, absolute zero offers insight. While we cannot approach it physically, understanding the principles it represents, minimal motion, energy preservation, and quantum constraints, illuminates the processes occurring in the coldest regions of space. It bridges the gap between human intuition and cosmic reality, connecting laboratory observations to molecular clouds, Bok globules, and the farthest reaches of interstellar space. Cold, therefore, is not abstract. It is measurable, meaningful, and deeply informative about the behavior of matter under the most extreme conditions. Studying absolute zero and near-zero temperatures also informs our understanding of entropy, order, and stability. As systems approach the lowest possible temperature, entropy approaches a minimum, molecules settle into their lowest energy configurations, and structures become highly stable. In cosmic environments, this principle governs the behavior of matter in cold regions, ensuring the preservation of molecules, the slow progression of reactions, and the stability of clouds and nebula over immense timescales. Cold is a regulator of order, a stabilizer of matter, and a silent architect of cosmic evolution. By exploring absolute zero, both conceptually and experimentally, we gain a deeper understanding of the limits of cold in the universe. We learn how temperature shapes molecular motion, chemical reactions, and the formation of stars, how energy is preserved or distributed, and how the extreme cold of space orchestrates the slow, deliberate evolution of matter. Cold, in this sense, is not merely absence. It is a force, a principle, and a condition that underlies the structure and behavior of the cosmos. The pursuit of understanding absolute zero also highlights the interplay between theory and observation. Quantum mechanics predicts residual motion even at 0 Kelvin. Laboratories approach these conditions experimentally, and cosmic observations reveal natural examples of extreme cold. Together, these perspectives allow us to understand the extremes of temperature across scales, from the smallest laboratory systems to the largest structures in space. Cold becomes a bridge between human understanding and the universe itself, connecting measurable phenomena to cosmic processes in a coherent framework. Finally, absolute zero emphasizes that even in the most extreme conditions, the universe operates under consistent laws. Temperature, motion, energy, and matter are interdependent, governed by principles that remain valid whether in a laboratory or in the farthest nebula. The concept of cold as a limit, as a baseline, and as a regulator helps us understand the extreme environments where matter behaves in unusual ways, where chemical reactions slow to near standstill, and where gravity can dominate to produce stars and galaxies. Cold is not merely a measure, it is an essential, active condition that shapes the cosmos from the smallest particles to the grandest structures. As we linger near the theoretical limit of absolute zero, the universe begins to reveal behaviors of matter that are profoundly different from anything we experience in daily life. In these extreme cold regions, from the Boomerang Nebula to the densest molecular clouds and the carefully controlled conditions of cryogenic laboratories, atoms and molecules enter states that defy conventional expectations. Ordinary solids, liquids, and gases give way to exotic forms of matter that follow the strange and subtle rules of quantum mechanics. These states, which emerge only in the presence of extreme cold, illustrate the incredible adaptability of matter, the universality of physical laws, and the delicate interplay between temperature, motion, and structure. One of the most remarkable phenomena observed in these cold environments is superfluidity. When certain liquids, particularly helium-4, are cooled to near absolute zero, they enter a phase in which they flow without viscosity. A superfluid can climb walls, seep through microscopic cracks, and circulate endlessly without losing energy. This behavior, while observed in laboratory conditions on Earth, provides insight into the kinds of behaviors that might occur naturally in the frigid depths of space, where molecular motion is suppressed and energy dissipation is minimal. Superfluidity demonstrates that extreme cold does not simply slow matter, but fundamentally changes how it interacts with forces, gravity, and its surroundings. Closely related to superfluidity is the formation of Bose-Einstein condensates. These occur when a group of atoms is cooled so close to absolute zero that they occupy the same quantum state, effectively behaving as a single, coherent entity. In this state, individual particles lose their distinct identities, merging into a collective whole that exhibits properties completely unlike those of warmer matter. Bose-Einstein condensates, first achieved in laboratories in the 1990s, highlight the profound influence of cold on quantum behavior. In cosmic regions approaching similar temperatures, matter can exhibit subtle collective phenomena, influencing the dynamics of dense clouds and the behaviour of molecules in ways that are only now beginning to be understood. Exotic states of matter in the coldest regions also extend to solids and crystals. At temperatures near absolute zero, materials can enter configurations that minimise energy, forming perfectly ordered lattices, superconducting phases, or unique magnetic structures. In superconductivity, electrons pair up and move through a material without resistance, allowing for the unimpeded flow of electricity. While this is studied in laboratories, the underlying principles may also influence the behaviour of charged particles in cosmic dust grains or the icy mantles of molecular clouds. Cold stabilises these structures, preserves order, and allows the manifestation of properties that are entirely absent at higher temperatures. In addition to laboratory analogues, the universe itself provides examples of matter in these exotic states. Within molecular clouds, dust grains coated with ices create surfaces where atoms and molecules interact in ways dictated by extreme cold. Motion is slow, collisions are rare, and quantum tunneling can dominate chemical reactions, allowing molecules to combine even when classical energy barriers would normally prevent it. This slow, deliberate chemistry enables the formation of complex organic compounds, water ice, and other molecular structures that may eventually become part of stars, planets, or even the seeds of life. Cold, in this sense, is a facilitator of structure, preserving matter in forms that would be unstable at higher temperatures. Even the faint gas of the Boomerang Nebula illustrates exotic behaviour in extreme cold. Expansion reduces kinetic energy to nearly negligible levels, slowing molecular motion and preserving fragile compounds that would otherwise disintegrate in warmer environments. The dynamics of such a nebula are influenced as much by temperature as by gravity or motion, demonstrating that cold is an active regulator of matter's behaviour. At 1 degree Kelvin, the subtle quantum properties of molecules become more significant, guiding interactions and determining the stability of structures on microscopic and macroscopic scales. Cold also affects the collective behaviour of particles. In extremely low temperature environments, gases can exhibit condensation phenomena without ever transitioning through conventional liquid phases. Quantum degeneracy pressures emerge, particle-wave duality becomes significant, and interactions that are negligible at higher temperatures dominate the dynamics of the system. These behaviours highlight the intricate relationship between energy, temperature, and structure, showing that cold is not merely a static absence, but a dynamic condition that reshapes matter, chemistry, and motion. The study of these states also illuminates the boundaries of what is possible in the universe. In everyday life, we observe solids, liquids, and gases behaving according to classical physics. In laboratories and in extreme cosmic environments, matter defies these classical expectations, revealing superfluidity, superconductivity, Bose-Einstein condensation, and other exotic phases. These states exist only because motion has been suppressed by extreme cold, allowing quantum effects to dominate. They serve as a reminder that temperature is not merely a number, it is a governing principle that defines the behaviour of matter, structures the evolution of systems, and determines the potential for complexity in both chemistry and physics. Even the chemical behaviour of molecules is transformed in these cold regions. Atoms that would rapidly vibrate, collide, or dissociate at higher temperatures instead adhere to surfaces, form clusters, and interact through quantum tunneling. Reactions that require high activation energy are suppressed, allowing delicate compounds to persist. Cold stabilizes matter, preserves molecular structures, and provides the conditions necessary for gradual cumulative processes that can take millions of years. In molecular clouds, for example, water, carbon monoxide, ammonia, and complex organics survive and interact thanks to the stabilizing influence of extreme cold. The interplay between exotic states and cosmic structure is also profound. In molecular clouds, the extreme cold maintains the stability of dense cores, allowing gravity to dominate and initiate the slow collapse that eventually produces stars. In the Boomerang Nebula, expansion-driven cooling creates conditions where matter moves so slowly that it approaches a near standstill, illustrating how temperature regulates motion, chemical interaction, and structural evolution. Cold in these contexts is a fundamental force shaping both the microscopic and macroscopic universe. Cryogenic laboratories on Earth mirror these conditions in miniature, allowing researchers to observe superfluidity, condensation, and quantum coherence. These experiments provide direct evidence for the principles inferred from cosmic observations, linking laboratory physics to the behavior of matter across the universe. The insights gained from these studies inform our understanding of how extreme cold influences molecular evolution, star formation, and the preservation of chemical complexity. Cold, therefore, is simultaneously a subject of study, a tool for observation, and a governing parameter in both laboratory and cosmic environments. Even at the smallest scales, extreme cold alters the very identity of matter. In Bose-Einstein condensates, individual atoms lose their distinct identities, behaving collectively as a single entity. This phenomenon demonstrates that cold is not only a measure of motion, but a transformative condition, capable of altering the fundamental behavior of particles. In cosmic terms, this implies that in regions approaching absolute zero, the quantum properties of matter become increasingly significant, guiding interactions, reactions, and the evolution of structures in subtle but essential ways. The influence of cold extends to energy storage and transfer. In exotic states, energy is preserved with minimal dissipation, allowing matter to remain in low-energy configurations for extended periods. This preservation is critical in molecular clouds and Bok globules, where chemical reactions are slow and gravitational collapse requires stability over millions of years. Cold is not inert. It is a regulator of energy, motion, and structure, ensuring that matter can evolve predictably and consistently under extreme conditions. Observationally, the exotic states of matter in cold regions are detected through subtle signals. Emission lines, absorption features, and the behavior of dust and gas reveal temperatures, densities, and quantum effects. Instruments sensitive to infrared, microwave, and submillimeter wavelengths allow scientists to measure the properties of matter at near absolute zero temperatures, translating faint signals into a comprehensive understanding of chemical and physical processes. Cold is both the condition being measured and the signal enabling measurement, linking extreme temperatures to our capacity to observe, understand, and interpret the cosmos. Even in the vast emptiness between stars, cold produces profound effects. While particle density is low, the slow motion and minimal energy of atoms and molecules enable processes such as molecular adhesion to dust grains, quantum tunneling, and the formation of simple compounds. Over millions of years, these processes accumulate, contributing to the chemical richness of the universe. Cold, in this sense, is both a preserver and a facilitator, maintaining stability while enabling the gradual emergence of complexity. In summary, the coldest regions of the universe reveal the extraordinary adaptability of matter. Superfluidity, Bose-Einstein condensation, superconductivity, and other exotic states emerge only when motion is suppressed by extreme cold, highlighting the subtle interplay of quantum mechanics, thermodynamics, and chemical stability. These phenomena, observed both in space and simulated in laboratories, demonstrate that cold is not merely an absence of heat, but an active force that shapes behavior, preserves structure, and enables processes over vast timescales. Even among the familiar structures of molecular clouds and Bok globules, there exist regions of profound mystery. Dense, cold pockets so dark that they absorb nearly all the light passing through them. These are the dark molecular clouds, often referred to as the hidden or secretive corners of the cosmos, where matter drifts slowly in near total silence, and the processes of star formation and chemical evolution unfold in extreme secrecy. Unlike the more luminous regions of space, these clouds are invisible in ordinary optical light, appearing as opaque silhouettes against brighter backgrounds. Yet within them, an astonishing variety of phenomena occur, all governed by extreme cold, low density, and the patient laws of physics. In these environments, cold is not merely a measure of temperature, but a defining condition that shapes motion, chemistry, and the evolution of entire star systems. Dark molecular clouds are composed predominantly of molecular hydrogen, along with helium, carbon monoxide, ammonia, water, and a host of more complex organic molecules. Their temperatures can be astonishingly low, often ranging from just a few degrees above absolute zero to around 10 Kelvin, creating conditions where atomic and molecular motion is exceedingly slow. At these temperatures, molecules cling to tiny dust grains, forming icy coatings that act as platforms for chemical reactions. Despite the extreme cold, these reactions can gradually produce increasingly complex molecules over millions of years, building a chemical richness that may ultimately become part of stars, planets, or even the raw materials for life. Cold in these clouds is not an absence but an active, governing influence, slowing motion while preserving structure and enabling the accumulation of chemical complexity. One of the remarkable aspects of dark molecular clouds is their opacity. Because they are so dense and cold, they absorb visible and ultraviolet light, making them nearly invisible to traditional telescopes. It is only through infrared, radio, and sub-millimeter observations that we can detect them, using the faint emission of molecules or the subtle absorption of background starlight. These techniques reveal not only the presence of the clouds, but also their temperature, density, and chemical composition. Observing the secretive interior of a dark molecular cloud requires sophisticated instruments and careful interpretation, translating faint signals into a detailed picture of matter, behaving in ways that challenge ordinary intuition. The extreme cold preserves these structures, allowing them to persist for millions of years without being disrupted by radiation or turbulence from nearby stars. The interiors of dark molecular clouds are often dynamic, despite their low temperatures. Turbulence, magnetic fields, and weak radiation fields create filaments, clumps, and cores, guiding the distribution of matter and determining where star formation will eventually occur. Cold ensures that thermal motion does not counteract gravitational collapse, allowing dense regions to slowly contract over extended timescales. The patient combination of low temperature and gravitational forces sets the stage for the birth of stars, the accumulation of chemical complexity, and the preservation of fragile molecules that might otherwise be destroyed. Cold is both a stabilizer and an enabler, maintaining structure while facilitating transformation over cosmic timescales. Within these dark clouds, chemistry proceeds in subtle but important ways. Icy dust grains serve as reaction sites for atoms and molecules that adhere to their surfaces, allowing hydrogen to combine with oxygen to form water, carbon to form hydrocarbons, and nitrogen to form ammonia and other compounds. Even quantum tunneling plays a role, allowing reactions to occur that would otherwise be energetically impossible at such low temperatures. The result is a slowly evolving chemical environment, rich in diversity, preserved by the extreme cold and hidden from direct observation. Cold ensures that molecules survive long enough to interact, accumulate, and contribute to the formation of new stars and planetary systems. Dark molecular clouds also illustrate the delicate balance between isolation and interaction. While their interiors are shielded from external radiation, cosmic rays, faint starlight, and occasional shock waves can penetrate, introducing localized energy that triggers chemical reactions or motion. These interactions, while minor in the overall energy budget, provide the subtle disturbances necessary for complexity to emerge. Cold dominates, ensuring stability, while small injections of energy allow evolution to proceed. The interplay of extreme cold with occasional perturbations creates an environment that is at once silent, dynamic, and fertile, a secret life hidden within the darkness of space. The structural organization of these clouds is influenced by both cold and gravity. Dense cores form as matter slowly drifts together, filaments channel gas into specific regions, and low temperatures prevent thermal pressure from dispersing the accumulating material. Over hundreds of thousands or millions of years, these cores may reach sufficient density to ignite nuclear fusion, giving birth to new stars. The surrounding cold environment continues to regulate the pace of chemical reactions and molecular motion, ensuring that the process is gradual and stable. Cold is therefore not passive. It is a critical factor in the timing, structure, and outcome of star formation within these secretive clouds. Observations of dark molecular clouds also reveal variations in temperature and density. While interiors may reach a few degrees above absolute zero, peripheral regions or areas influenced by nearby stars can be slightly warmer. This temperature gradient influences the distribution of matter, the stability of chemical compounds, and the onset of star formation. Cold establishes the baseline, preserving structure and enabling processes, while local variations provide the conditions necessary for evolution and complexity. Temperature, in this context, is both a global regulator and a local influencer, shaping the secret life of these clouds across multiple scales. Even the faintest emissions from molecules in dark clouds provide insight into their extreme cold. By analysing the spectral lines of carbon monoxide, ammonia, and other trace molecules, astronomers can infer temperature, density, and motion within these clouds. The signals are subtle, requiring sensitive detectors, long observation times, and careful calibration. Yet these measurements reveal a wealth of information about how cold regulates molecular behaviour, guides gravitational collapse, and preserves chemical complexity. Cold is both the condition and the signal, allowing scientists to understand processes that unfold in extreme isolation and over vast timescales. Dark molecular clouds are also laboratories for understanding the relationship between cold and time. At such low temperatures, processes unfold slowly. Molecular motion is sluggish, chemical reactions progress gradually, and gravitational collapse occurs over millions of years. Cold imposes a deliberate pace, ensuring that matter evolves predictably and preserving the conditions necessary for the formation of stars and planetary systems. These clouds demonstrate that extreme cold is not static or inert. It is a regulator of the cosmic clock, dictating the timing of events and the progression of complexity in a manner that is subtle, deliberate, and measurable. The extreme cold of these clouds also preserves fragile molecular structures. Organic compounds, water ice, and other molecules remain stable, adhering to dust grains or forming clusters that may eventually be incorporated into new stars or planets. This preservation is essential for the chemical richness of the universe, enabling processes that can ultimately contribute to the emergence of life. Cold, in this sense, acts as a conservator, slowing destructive processes while facilitating the accumulation of chemical diversity and the preparation of matter for future evolution. Even in their apparent stillness, dark molecular clouds are dynamic systems. Filaments stretch across light years, turbulence introduces motion, and magnetic fields guide matter along invisible paths. Cold suppresses thermal motion, ensuring stability, while gravity and other forces induce slow, deliberate movement. This combination of extreme chill and gentle dynamics creates conditions uniquely suited for the birth of stars, the preservation of molecules, and the orchestration of processes that shape the cosmos. Cold is the silent architect of structure, guiding matter with precision and patience. The secret life of these clouds also emphasizes the universality of cold as a governing principle. Whether in laboratory simulations, Bock globules, molecular clouds, or the Boomerang Nebula, extreme cold regulates motion, preserves structure, and enables chemistry. It is a condition that allows matter to evolve over vast distances and timescales, providing the stability necessary for the gradual emergence of stars, planets, and molecular complexity. Cold is both a local condition and a cosmic regulator, influencing behavior on scales from microscopic particles to entire star-forming regions. By studying dark molecular clouds, scientists gain insight into processes that are otherwise hidden from view. The extreme cold, combined with isolation and density, creates conditions in which matter behaves predictably, chemistry proceeds slowly, and gravitational collapse can occur without disruption. Observations in the infrared, submillimeter, and radio wavelengths allow researchers to map temperature, density, and motion, revealing the hidden life within these dark, frigid environments. Cold, in this sense, is both the canvas and the brush, shaping the behavior of matter while providing the signals necessary for understanding. Even the faintest variations in temperature within dark molecular clouds have profound implications. Slightly warmer regions near forming stars can trigger chemical reactions, induce motion, or influence the collapse of dense cores. Yet the pervasive cold ensures that these processes are gradual, stable, and predictable. Temperature is both a background condition and a dynamic factor, regulating the secret life of matter in these hidden corners of the universe. Dark molecular clouds remind us that cold is not merely an absence of heat. It is an active, pervasive force that structures matter, preserves molecules, regulates motion, and orchestrates the slow, deliberate evolution of the cosmos. These hidden, frigid regions, invisible to ordinary sight, contain the seeds of stars and planets, the foundations of chemical complexity, and the processes that enable cosmic structure to emerge over millions of years. Cold is the silent governor, the patient architect, and the essential condition that makes the secret life of these clouds possible. As we explore the coldest reaches of the universe, we encounter an enigmatic phenomenon where cold, heat, and gravity converge in ways that defy intuition: black holes. These cosmic objects, formed from the collapse of massive stars or through the merging of dense matter, are often thought of as inescapable voids from which nothing, not even light, can escape. Yet when we consider temperature in the context of black holes, an extraordinary paradox emerges, one that challenges conventional notions of hot and cold, energy and entropy, and the very nature of matter and radiation. Black holes are, in some senses, both the ultimate reservoirs of energy and the deepest wells of cold, a duality that illuminates the subtle, counterintuitive ways temperature manifests in the cosmos. A black hole, by its classical definition, is defined by its event horizon, a boundary beyond which escape is impossible. The interior, hidden from view, is thought to contain matter compressed into an extraordinarily dense singularity, where conventional physics breaks down. The temperature of a black hole, however, is not determined by this hidden core, but by a phenomenon predicted in the 1970s by Stephen Hawking. Black holes radiate energy in the form of what is now known as Hawking radiation. This radiation is incredibly faint for large black holes, such as those formed from stellar collapse, and corresponds to extremely low temperatures, far below those of the cosmic microwave background. In this sense, black holes, despite their immense energy content, can be extraordinarily cold objects, blending extremes in ways that seem paradoxical. Hawking radiation arises from the interplay between quantum mechanics and gravity near the event horizon. In the vacuum of space, particle-antiparticle pairs constantly form and annihilate, a subtle fluctuation dictated by the uncertainty principle. Near the event horizon, one particle can fall into the black hole while the other escapes, creating a faint emission of radiation that carries energy away from the black hole. The temperature associated with this radiation is inversely proportional to the mass of the black hole. Larger black holes are colder, while smaller black holes are hotter. This relationship is striking because it implies that the most massive black holes, which contain incredible amounts of matter and energy, have temperatures approaching absolute zero. Cold, in this context, is not merely a measure of thermal energy, but a reflection of mass, gravity, and quantum processes in extreme conditions. The paradox of temperature in black holes challenges intuition. Here is an object with immense gravitational energy, compressing matter to densities beyond comprehension, yet its thermal radiation is incredibly weak, corresponding to a temperature far colder than anything found in interstellar clouds, or even the Boomerang Nebula. At the same time, smaller black holes, such as primordial black holes hypothesized to have formed in the early universe, could be extremely hot, emitting radiation at levels detectable across cosmic distances. Cold and heat, therefore, are relative, depending not on conventional energy content but on the interplay of mass, gravity, and quantum processes. The universe reveals that temperature is not absolute, that it is a nuanced concept, and that cold can emerge even in the presence of enormous energy. Even the largest black holes, with masses millions or billions of times that of the Sun, radiate at temperatures of fractions of a microkelvin, colder than the cosmic microwave background. This means that in a universe filled with radiation at 2.7 Kelvin, these black holes absorb more energy from the environment than they emit, effectively acting as net cold objects. Their interaction with surrounding space is dominated by absorption rather than emission, reinforcing the idea that cold is not merely a relative measure, but a condition shaped by both local environment and intrinsic properties. The interplay of cold, radiation, and gravity creates a dynamic equilibrium that governs the behavior of these extreme objects. Black holes also illustrate the relationship between cold, entropy, and time. While their emitted radiation is faint and cold, the entropy of a black hole is enormous, proportional to the area of the event horizon rather than the volume of the interior. This implies that cold objects can contain vast amounts of hidden information, a principle that has profound implications for thermodynamics, information theory, and our understanding of the universe. Cold is, in this sense, not an absence of complexity, but a stabilizing backdrop against which information, energy, and quantum processes interact. The paradox of black hole temperature demonstrates that cold can coexist with extreme density, gravitational dominance, and hidden potential, revealing the subtlety and richness of the concept of temperature in the cosmos. The study of black hole temperatures also informs our understanding of cosmic evolution. Black holes slowly lose mass through Hawking radiation, a process so gradual that for stellar mass black holes it would take timescales far exceeding the current age of the universe to evaporate significantly. During this process, their temperature slowly rises as mass decreases, eventually accelerating toward higher energies for the smallest black holes. This dynamic illustrates that cold is not static. It evolves, interacting with mass, gravity, and quantum phenomena. Temperature is a regulator, a recorder of change, and a guide to the long-term fate of some of the most extreme objects in the universe. Observationally, measuring the temperature of black holes is indirect. Hawking radiation is extraordinarily faint for stellar and supermassive black holes, making direct detection nearly impossible with current technology. Instead, scientists rely on theoretical models grounded in quantum mechanics and general relativity, combined with observations of the environment near black holes. Accretion disks, relativistic jets, and surrounding gas provide clues about energy transfer, gravitational dynamics, and thermal processes. While the black hole itself may be colder than the surrounding space, its interactions influence nearby matter, creating gradients of temperature and energy that are both observable and informative. The paradox of temperature also extends to the concept of absolute zero. While the surface of a large black hole may approach microkelvin levels, it cannot reach absolute zero, just as no laboratory system can. Quantum effects ensure that motion and energy fluctuations persist, and Hawking radiation guarantees that even the coldest black holes are not perfectly inert. Cold, therefore, is always relative, a subtle interplay between classical energy, quantum behaviour, and environmental context. It serves as a reminder that the extremes of temperature are governed not only by thermal energy, but also by the fundamental rules of physics operating at the limits of understanding. Even in the context of cosmic structure, black holes demonstrate the influence of cold. Supermassive black holes anchor galaxies, affecting the motion of stars, gas, and dust across vast distances. Their low temperature does not diminish their gravitational dominance, illustrating that cold can coexist with immense influence. Temperature, motion, and energy interact in ways that are nuanced, revealing that cold is not merely absence or weakness, but a parameter that shapes dynamics across scales from microscopic to galactic. The paradox of black hole temperature also provides insight into the interplay between energy and information. While Hawking radiation is faint and cold, it carries information about the black hole's internal state, linking temperature to entropy and quantum processes. Cold becomes a conduit through which matter, energy, and information are connected, demonstrating that temperature is deeply tied to the fundamental structure of the universe. The faint chill of a black hole encodes complexity, preserves potential, and mediates the slow evolution of mass and energy in a manner that is simultaneously subtle and profound. Even for smaller black holes, hypothetical or primordial, the reverse occurs. As mass decreases, the black hole heats up, eventually radiating significant energy in the form of high-energy particles and photons. Cold and heat are thus intertwined, dependent on mass, energy distribution, and quantum effects. The extremes of temperature illustrate that the universe operates on principles that defy simple categorization, where cold can coexist with enormous energy, and where heat can emerge from objects that were once frigid and quiescent. In summary, black holes exemplify the paradoxical nature of temperature in the universe. They can be among the coldest objects known, emitting faint radiation at microkelvin levels, yet they contain immense gravitational energy, compress matter beyond comprehension, and influence their surroundings on cosmic scales. Cold in this context is not a limitation, but a principle that governs stability, energy exchange, and the long-term evolution of matter. It demonstrates that temperature, far from being a simple measure, is a nuanced dynamic parameter, intricately linked to gravity, quantum mechanics, and the hidden structure of the cosmos. Beyond the dense regions of galaxies, beyond the star-filled disks and the clusters of molecular clouds, lies intergalactic space, the vast, cold, almost unimaginable expanse between galaxies. It is a realm dominated by emptiness, sparsely populated by a few scattered atoms, tenuous gas, and dark matter that silently shapes the motion of everything around it. Intergalactic space is, in many ways, the ultimate expression of cosmic cold, a nearly perfect vacuum in which temperatures are defined more by the faint whispers of radiation than by the motion of particles. Here, matter drifts slowly over millions of light years, collisions are incredibly rare, and energy exchange occurs only through subtle interactions, creating conditions that stretch human comprehension and challenge our perception of what cold truly is. The temperature in intergalactic space is largely determined by the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates the universe. This radiation provides a baseline of roughly 2.7 Kelvin, establishing the coldest pervasive environment in which matter exists over enormous distances. Unlike the interiors of molecular clouds or Bok globules, where dense gas and dust create localized cold pockets, intergalactic space is almost entirely empty, containing, on average, less than 1 atom per cubic meter. Despite this extreme sparsity, these few atoms and particles exist in a delicate equilibrium, influenced by the faint radiation of the cosmic microwave background, occasional cosmic rays, and the gravitational influence of nearby galaxies or clusters. Cold in this context is absolute in its consistency, yet subtle in its expression. shaping the behaviour of matter across vast stretches of time and space. The coldness of intergalactic space has profound consequences for the behaviour of matter. Without frequent collisions, particles move independently, drifting for millions of years without interacting. Thermal motion is minimal, meaning that any chemical reactions, molecular formation, or energy redistribution occurs at rates that are essentially negligible on human timescales. Yet, even in this extreme cold, gravity continues to act, subtly guiding the motion of gas, stars and galaxies, slowly assembling clusters, filaments, and large-scale structures that define the cosmic web. Cold here is not simply an absence of warmth. It is a fundamental factor that allows the universe to organise itself on scales that are both vast and enduring. Even the most tenuous gas in intergalactic space is influenced by cold. Hydrogen, the most abundant element in the universe, exists largely as individual atoms or low-density clouds, moving sluggishly in response to gravity and radiation. Helium, electrons, and trace elements behave similarly, their kinetic energy minimal due to the extremely low temperatures. These conditions contrast sharply with the warmer regions within galaxies, where stellar radiation, supernovae, and cosmic events inject energy into the surrounding medium. Cold, in intergalactic space, dominates the dynamics, ensuring stability while allowing the long-term evolution of structures dictated by gravity and large-scale motion. The cosmic web, the intricate network of filaments, voids, and galaxy clusters that stretches across billions of light-years, owes much of its structure to the interplay of gravity and cold. In the vast voids between filaments, temperatures are exceedingly low, approaching the baseline set by the cosmic microwave background. Here, matter is sparse, motion is slow, and interactions are minimal. Gravity acts over these long distances, slowly drawing material into filaments and nodes where galaxies eventually form. Cold ensures that the diffuse gas remains stable during these vast journeys, preserving the conditions necessary for the large-scale architecture of the universe. In this sense, extreme cold is a silent architect, shaping the arrangement of matter on the grandest scales imaginable. Even isolated pockets of gas within intergalactic space can provide insight into the effects of cold. Observations using radio and ultraviolet spectroscopy reveal clouds of hydrogen that drift between galaxies, illuminated faintly by distant starlight. These clouds are incredibly cold, with temperatures near the cosmic background, and they preserve chemical compositions that reflect processes occurring billions of years ago. Cold stabilizes these structures, ensuring that molecules and atoms persist, providing a record of cosmic history. Studying them allows scientists to trace the movement of matter, the evolution of galaxies, and the interactions of large-scale structures across time. Intergalactic space also demonstrates the subtle influence of cold on energy distribution. Without frequent collisions, thermal energy cannot propagate effectively through the medium. Photons from distant galaxies, quasars, or the cosmic microwave background become the primary means of energy transfer. Even a single photon travelling millions of light-years can influence the ionization state of an atom, subtly altering the properties of gas in these extreme environments. Cold dictates the behaviour of matter, not by active force, but by restraint, limiting motion, preserving structure, and allowing gravity and radiation to shape the universe with measured precision. The near absolute zero conditions of intergalactic space also have implications for the formation of large-scale structures. Gas in the voids moves slowly, drifting under the influence of gravity, coalescing into filaments over billions of years. Galaxies form along these filaments, drawing matter from the cold, sparse medium surrounding them. Even the faintest interactions, such as minor heating from radiation or shock waves from distant supernovae, are moderated by the pervasive cold, ensuring that changes occur gradually, predictably, and in a manner consistent with the long-term evolution of the cosmos. Temperature here is not a force but a governor, regulating motion and providing stability over immense spatial and temporal scales. Even dark matter, which dominates the mass of the universe but interacts primarily through gravity, is indirectly influenced by the cold, sparse environment of intergalactic space. While dark matter does not interact thermally in the same way as ordinary matter, the distribution of baryonic matter, hydrogen, helium and other elements, is shaped by both gravity and temperature. Cold allows gas to remain diffuse, slow-moving and stable, ensuring that it can trace the gravitational potential of dark matter, ultimately shaping the cosmic web and influencing the formation and evolution of galaxies. In this way, extreme cold in intergalactic space has consequences not only for the matter we can see, but also for the underlying structure of the universe itself. Even the passage of time is affected by cold. Processes that would be rapid in warmer, denser regions occur exceedingly slowly here. Chemical reactions are negligible, molecular formation is minimal, and energy exchange is subtle. Cold imposes a deliberate rhythm on the evolution of the universe, stretching events across billions of years. Star formation, galactic interactions, and the movement of matter within the cosmic web are all regulated in part by the low temperatures that define intergalactic space. Temperature, then, is a regulator of pace, as well as a measure of energy, shaping the evolution of the universe with patience and precision. Observations of intergalactic space reveal the influence of cold on the ionization state of matter. Even with sparse ultraviolet radiation from distant galaxies, the low density and extreme temperatures mean that most atoms remain neutral or weakly ionized. These conditions contrast sharply with the warmer interstellar medium within galaxies, where collisions and radiation maintain higher ionization levels. Cold here ensures stability, preserves structure, and provides a nearly pristine environment for observing the subtle interactions of matter, radiation, and gravity over cosmic distances. Even the faint filaments of the cosmic web, which span millions of light years, are defined in part by the pervasive cold. Gas within these filaments is cool and tenuous, moving slowly under gravitational influence, forming the skeleton upon which galaxies are assembled. Temperature regulates the behavior of this matter, preventing rapid dispersion, allowing accumulation in denser regions, and guiding the gradual formation of large-scale structures. Cold, in this context, is both a constraint and a facilitator, ensuring the universe evolves in a measured, deliberate manner over billions of years. The vast emptiness of intergalactic space also illustrates the universality of cold. From the icy interiors of Bok globules to the near absolute zero of the Boomerang Nebula, to the sparsity between galaxies, cold governs behavior across scales. It slows motion, preserves matter, regulates chemical reactions, and provides stability, ensuring that matter can evolve predictably. Even in regions with only a few particles per cubic meter, cold exerts its influence, shaping the structure, motion, and evolution of the universe in ways that are subtle, pervasive, and essential. Ultimately, intergalactic space represents the most extreme cold that is widespread and persistent. The temperatures dictated by the cosmic microwave background, interactions with faint radiation, and the near vacuum of the medium maintain matter in a delicate balance. Cold stabilizes sparse gas, preserves chemical composition, slows motion, and governs the evolution of matter on cosmic scales. In this vast, silent expanse, the universe stretches to its limits, and the subtle, persistent influence of cold becomes apparent, orchestrating structure, regulating dynamics, and enabling the slow, patient unfolding of cosmic history. Among the countless wonders of our own solar system, a number of worlds exist that are defined by ice, frost, and deep, unyielding cold. These frozen planets, moons, and dwarf planets offer a glimpse into extreme temperatures much closer to home, yet they are still profoundly colder than anything we experience on Earth. Unlike interstellar space, where cold is nearly absolute and matter is sparse, the frozen worlds of the solar system contain solid surfaces, thick ice layers, and thin, tenuous atmospheres, providing a laboratory for observing how extreme cold interacts with planetary geology, chemistry, and potential habitability. The conditions found here vary from the frigid outer layers of Mercury-shadowed craters to the frozen expanses of Pluto, from the icy moons orbiting Jupiter to the distant objects of the Kuiper Belt. Each location presents a unique interplay of temperature, radiation, and composition, revealing the diversity of cold within a single planetary system. One of the most striking examples of extreme cold is Pluto. Located on the outer edge of the solar system, Pluto's surface temperature averages around 44 Kelvin, which is roughly minus 229 degrees Celsius. At such low temperatures, nitrogen, methane, and carbon monoxide exist primarily in frozen states, forming vast plains, icy mountains, and delicate frost layers that subtly shift over time. Seasonal changes driven by Pluto's elongated orbit and axial tilt cause sublimation and deposition of these volatile ices, yet the extreme chill ensures that molecular motion remains minimal. These slow processes, occurring over decades or centuries, illustrate how cold regulates surface dynamics, chemical interactions, and even the potential for transient atmospheric phenomena on frozen worlds. The moons of the outer planets provide additional examples of extreme cold in action. Europa, orbiting Jupiter, is covered in a thick layer of ice, beneath which a subsurface ocean is believed to exist. Temperatures on the icy surface hover around 102 Kelvin, preserving water in solid form while allowing for minimal sublimation. Ganymede and Callisto, also moons of Jupiter, exhibit similar conditions, with ice dominating the landscape and chemical processes proceeding at glacial rates. Saturn's moon Enceladus presents a slightly different picture. Its surface averages around 75 Kelvin, yet localized heating from tidal forces produces geysers that eject water vapor and ice particles into space. Even here, the extreme cold shapes surface structures, maintains frozen deposits, and regulates the behavior of both ice and embedded organic compounds. In the realm of the Kuiper Belt, worlds like Haumea and Makemake showcase the persistence of cold over billions of years. These distant objects receive minimal sunlight, and their surfaces remain frozen at temperatures around 30 to 50 Kelvin. Methane and nitrogen ices dominate, creating reflective surfaces that slowly evolve through sublimation and deposition. Even over vast timescales, the extreme cold slows molecular motion, preserves volatile compounds, and maintains surface features with remarkable stability. Cold acts as both a preserver and regulator, shaping the evolution of these distant, icy worlds in ways that are both subtle and enduring. Ice is not uniform across these worlds. Layers of water, methane, nitrogen, and carbon monoxide ice interact in complex ways, influenced by surface composition, radiation, and temperature gradients. In some regions, sublimation occurs as sunlight strikes the surface, while in permanently shadowed craters, temperatures remain near absolute minimums, preserving volatile ices for eons. The interplay between minimal heating and pervasive cold creates a delicate equilibrium where surface processes are extremely slow, motion is limited, and molecular behavior is highly constrained. Even slight variations in temperature can produce gradual but measurable changes in surface structure and composition. The study of these frozen worlds also provides insight into cryogeology, the science of ice-driven landscapes. On icy moons and dwarf planets, glaciers, tectonic-like fractures, and sublimation-driven formations shape surfaces in ways reminiscent of Earth's glacial regions, but under far colder conditions. Nitrogen and methane ices behave differently from water ice, creating smooth plains, rugged mountains, and complex patterns that evolve over centuries or millennia. The extreme cold ensures that deformation occurs slowly, molecular motion is restricted, and energy transfer is minimal. cold is a defining factor, regulating the pace of geological and chemical evolution, even in environments with very low energy input from sunlight. Atmospheric dynamics on these frozen worlds are equally influenced by extreme cold. Pluto, for example, exhibits a thin atmosphere composed primarily of nitrogen, with traces of methane and carbon monoxide. During periods of sublimation, surface ices convert into vapour, creating a tenuous cold atmosphere that remains in delicate balance. Temperatures dictate the rate of sublimation, condensation, and atmospheric collapse, controlling the seasonal behaviour and chemical interactions. Cold, therefore, extends beyond the surface, influencing the motion, stability, and composition of the atmosphere in ways that are subtle yet critical to the overall behaviour of these worlds. Even the inner reaches of the solar system present microcosms of cold extremes. Mercury's polar craters, permanently shadowed from the sun, maintain temperatures around 100 Kelvin, preserving water ice despite the planet's otherwise scorching surface. These pockets of cold, isolated and stable, illustrate the interplay between shadow, heat and cryogenic preservation. Cold dominates, ensuring that water ice can persist for millions of years even in proximity to extreme solar radiation, providing a tangible example of how temperature dictates the behaviour and longevity of matter in diverse environments. The outer solar system is particularly revealing because these frozen worlds interact with radiation and gravitational forces while remaining extremely cold. Jupiter's radiation belts, Saturn's faint magnetic environment, and the weak sunlight reaching the Kuiper belt all introduce minor energy inputs, yet temperatures remain sufficiently low that molecular motion is limited and surface chemistry proceeds slowly. Cold ensures stability, allowing ice to persist, complex molecules to survive, and geological structures to evolve over incredibly long timescales. This delicate balance between energy input and extreme cold creates conditions that are both static and dynamic, preserving matter while allowing gradual evolution. Cold also influences the potential for habitability on these distant worlds. While surface conditions are too extreme for known life, subsurface oceans, such as those hypothesized beneath Europa's and Enceladus's ice, are insulated by the surrounding ice and maintained in liquid form through tidal heating and residual geothermal energy. The extreme cold of the outer layers preserves these subsurface oceans, minimizing energy loss and stabilizing chemical gradients that could potentially support microbial life. Here, cold is not merely a limitation, it is a protector, preserving environments over geological timescales while moderating energy transfer. In studying these frozen worlds, scientists rely on a combination of direct observation, spectroscopy, spacecraft missions, and theoretical modelling. Surface temperatures are inferred from infrared emission, sublimation rates, and reflective properties of ices, while chemical composition is determined through spectral analysis and detection of molecular signatures. Cryogeological features such as ice mountains and glaciers are mapped using high-resolution imaging from orbiters and flyby missions. Each observation reveals how cold shapes the physical, chemical, and dynamic properties of these worlds, providing a window into the interplay between temperature, motion, and time in environments far removed from the warmth and familiarity of Earth. Even minor variations in temperature across these frozen surfaces can produce long-term changes, as ices sublimate or condense, as chemical reactions occur at slow rates, and as radiation subtly alters molecular bonds. Cold ensures that evolution proceeds at an almost imperceptible pace. Geological and chemical changes accumulate gradually, preserving patterns that reveal the history of the world over millions or billions of years. Cold is both a regulator and a conservator, shaping behaviour, preserving structure, and allowing processes to unfold slowly in accordance with the underlying laws of physics. The diversity of frozen worlds within our solar system also illustrates the range of cold environments. from the water ice-dominated surfaces of Europa and Enceladus to the methane and nitrogen ices of Pluto and Triton, from permanently shadowed craters on Mercury to distant Kuiper belt objects, temperatures vary, yet all remain far below what we experience on Earth. Cold defines the behaviour of matter in each case, slowing motion, preserving molecules, and regulating geological and chemical evolution. It is a pervasive influence, shaping the physical and chemical landscapes of these worlds in ways that are both subtle and profound. The frozen worlds of the solar system provide a bridge between the cold extremes of interstellar space and the environments we can study directly. They demonstrate how low temperatures influence surface chemistry, ice behaviour, atmospheric stability, and geological processes. They reveal the interplay between radiation, gravity, and cryogenic conditions, and they illustrate the universality of cold as a governing principle, whether in molecular clouds, bog globules, or the distant reaches of the Kuiper belt. These worlds remind us that cold is not merely an absence of heat, but a force, a regulator, and a preserver, orchestrating the slow, deliberate evolution of matter on planetary scales while connecting to the larger cosmic story. Within the vast, frigid stretches of space, cold plays a role far more profound than simply preserving matter or slowing molecular motion. It acts as a cosmic architect, shaping the very processes that lead to the formation of stars and planets. In regions where temperatures hover just a few degrees above absolute zero, gravity, chemistry, and cold work in concert, orchestrating the slow, deliberate transformation of diffuse gas and dust into structured, luminous systems. Cold regulates motion, stabilizes clouds, and allows the gradual accumulation of mass, making it an essential component in the life cycle of celestial bodies. Understanding this role provides a lens through which we can view the universe not only as a place of extremes, but as a finely tuned system governed by temperature, energy, and time. At the heart of star formation are molecular clouds, dense accumulations of gas and dust, where temperatures are low enough to permit the slow aggregation of matter. Cold minimizes thermal pressure, allowing gravity to dominate and initiate the collapse of dense cores. Within these cores, matter begins to condense, motion slows, and chemical processes proceed gradually. This delicate balance ensures that stars form in a controlled manner rather than dissipating into the surrounding medium. Without the stabilizing influence of extreme cold, molecular clouds would remain diffuse, unable to coalesce into the dense structures required for stellar birth. Temperature, therefore, is not merely a backdrop but a governing factor, determining both the timing and outcome of star formation. The process is gradual, spanning millions of years. As a dense core contracts under gravity, the surrounding cold gas continues to shield it from disruptive forces, maintaining structural integrity and regulating the flow of energy. Cooling mechanisms such as radiation emission from molecules and dust grains allow the core to shed excess energy, further supporting collapse. Cold enables this slow energy dissipation, preventing thermal pressure from halting the process and ensuring that contraction can proceed toward the critical densities required for nuclear fusion. In this sense, cold serves both as a facilitator and a regulator, allowing the universe to construct stars with precision over immense timescales. Chemistry within these cold regions is equally critical. At extremely low temperatures, molecules adhere to dust grains, forming icy mantles that act as sites for additional reactions. Hydrogen combines with oxygen to produce water ice, carbon and nitrogen form simple organic molecules, and complex molecules can assemble over millions of years. These reactions, slow and deliberate due to the frigid conditions, lay the groundwork for the chemical diversity observed in planetary systems. Cold preserves these molecules, ensuring they survive long enough to be incorporated into forming stars and protoplanetary disks. In this way, temperature is both a stabilizer and an enabler, shaping not only physical structure but also chemical evolution. Protoplanetary disks which form around young stars also owe their structure to cold. The outer regions of these disks remain extremely cold, often just a few tens of Kelvin, allowing volatile compounds like water, ammonia, and methane to freeze into solid ice grains. These icy particles collide and stick together, gradually building larger bodies such as planetesimals and eventually planets. The low temperature slows motion, reducing disruptive collisions and enabling accretion over millions of years. Cold, therefore, directly influences the architecture of planetary systems, determining the composition of planets, the distribution of volatiles, and the potential for habitable conditions on emerging worlds. Even the migration of material within these disks is governed by temperature. In colder regions, molecular motion is limited, viscosity is reduced, and material moves slowly toward the star or remains in stable orbits. This slow movement preserves chemical gradients, allowing differentiation between rocky inner planets and icy outer planets. Cold sets the pace for accumulation, growth, and compositional stratification, guiding the development of diverse planetary systems. The extreme chill is not simply a passive condition. It is an active participant in the construction of complex celestial architectures. Tidal forces, radiation from nearby stars, and shock waves from supernovae can introduce energy into these cold regions. Yet the pervasive low temperatures ensure that the processes remain gradual and controlled. Cold maintains stability, allowing gravity to dominate and accretion to proceed without disruption. It also preserves the chemical integrity of molecules, enabling the long-term evolution of complex compounds that may later contribute to planetary atmospheres, oceans, and potentially the seeds of life. In this sense, cold is simultaneously protective, regulatory, and creative, shaping the evolution of matter in multiple dimensions. Even the densest regions of molecular clouds illustrate the importance of temperature in star formation. In these cores, temperatures often reach just 10 Kelvin or lower, slowing molecular motion and allowing gravity to draw material inward. The combination of cold and density sets the rate of collapse, regulates the formation of protostars, and ensures that the surrounding environment remains stable. Chemical reactions occur slowly, volatile compounds are preserved, and energy is radiated away in a controlled manner. Cold thus governs both the pace and the nature of the formation process, ensuring that stars emerge with the physical and chemical conditions necessary for the eventual formation of planetary systems. In regions where multiple protostars are forming, cold regulates interactions between them. Low thermal energy prevents excessive dispersion of matter, allowing gravitational interactions to shape the architecture of stellar clusters. Cold slows the movement of gas and dust, enabling the slow redistribution of material, the preservation of molecular complexity, and the gradual emergence of structured systems. The interplay between temperature and gravity ensures that stars form in a manner that balances isolation with interaction, creating clusters, associations, and binary systems that are common in the galaxy. Observations of these regions through infrared, microwave, and radio telescopes reveal how cold dictates the behavior of matter. Molecular emission lines, dust continuum radiation, and subtle absorption features provide insight into temperature, density, and motion within star-forming clouds. These measurements allow astronomers to map the distribution of cold material, understand the dynamics of collapse, and trace the chemical evolution of gas and dust. Cold is both a measurable property and a controlling factor, linking observational data to the physical principles that govern star and planet formation. Even the smallest fluctuations in temperature within these clouds can have significant consequences. Slightly warmer regions may experience faster chemical reactions, increased sublimation of ices, or changes in the dynamics of collapse, while colder pockets preserve molecular structures and slow the pace of evolution. Temperature gradients create diversity within molecular clouds, guiding the formation of stars of different masses, protoplanetary disks of varying composition, and planetary systems with distinct characteristics. Cold thus introduces both stability and variation, shaping the universe with precision and subtlety. In protoplanetary disks, the outer cold regions act as reservoirs of volatile materials. Ices formed at low temperatures migrate inward as bodies accrete, contributing to the composition of forming planets. Cold ensures that these ices remain intact until they are incorporated into larger bodies, influencing planetary atmospheres, surface chemistry, and the distribution of water and organics. The preservation of these compounds through extreme chill demonstrates how cold directly shapes the chemical and physical evolution of emerging planetary systems. Even on the scale of entire star-forming regions, cold is essential. Filaments of dense gas, often just a few degrees above absolute zero, channel material into cores, regulate motion, and maintain stability. Gravity interacts with these cold filaments to concentrate mass, enabling the sequential formation of stars and clusters. Chemical complexity accumulates gradually, and thermal pressure remains low, ensuring that the overall structure of the cloud remains coherent. Cold is both a condition and a guiding influence, shaping the evolution of matter across multiple scales, from molecules to stars. The influence of cold extends to the timing of formation events. In warm regions, turbulence and thermal motion can disrupt collapse, prevent accretion, and hinder chemical evolution. In cold regions, these processes slow, allowing matter to accumulate, molecules to persist, and gravity to dominate. The pace of star and planet formation is therefore intimately tied to temperature, with cold acting as a regulator that stretches cosmic evolution over millions of years. This slow rhythm ensures that structures form gradually, processes unfold predictably, and chemical complexity is preserved for future generations of stars and planets. The role of cold in star and planet formation is profound. It governs motion, stabilizes matter, preserves chemical integrity, regulates energy, and orchestrates the timing of processes across vast distances and timescales. Cold is both subtle and powerful, influencing behavior on microscopic scales, guiding aggregation on planetary scales, and shaping the architecture of entire stellar systems. From molecular clouds to protoplanetary disks, from icy outer regions to the densest collapsing cores, cold is the silent architect of cosmic creation, ensuring that stars and planets emerge with the structure, composition, and potential for complexity that defines our universe. Gazing into the coldest reaches of space is like peering through a timeless window, offering a glimpse into the earliest moments of our universe. Temperature, often thought of simply as warmth or chill, becomes in this context a recorder of history, preserving the conditions that prevailed when matter first began to coalesce, when the first atoms formed, and when radiation decoupled from matter. The extreme cold of interstellar clouds, the persistent chill of the cosmic microwave background, and the freezing voids between galaxies all serve as markers of cosmic time, allowing us to reconstruct the evolution of the universe from its infancy to the intricate structures we observe today. In this sense, cold is not merely a physical property, it is a messenger from the past, a subtle signal that carries the story of creation across billions of years. The cosmic microwave background, a pervasive bath of radiation at just 2.7 Kelvin, is perhaps the clearest example of cold as a window into the early universe. This faint glow, the afterimage of the Big Bang, permeates all of space, providing a baseline temperature that defines the minimum energy present in the cosmos. Each photon of this radiation carries information about the density, composition, and motion of the universe when it was only a few 100,000 years old. Tiny fluctuations in this afterglow reveal the seeds of galaxies and clusters, showing how the cosmos evolved from a nearly uniform plasma into the intricate cosmic web of today. Cold, in this context, is a medium for preserving memory, encoding the earlier structures and conditions in the subtle energy of radiation. Beyond the cosmic microwave background, molecular clouds and dark clouds serve as long-term archives of cosmic history. The extreme chill in these regions slows molecular motion, preserving compounds, ices, and chemical interactions that may date back billions of years. Dust grains within these clouds hold traces of primordial elements and isotopes, providing clues to the processes that shape the formation of stars and planets. Cold ensures that this molecular heritage is maintained, acting as both conservator and regulator, stabilizing matter while allowing gradual evolution over immense timescales. In this way, observing cold regions is akin to reading the universe's diary, one carefully preserved in the language of temperature, density, and molecular composition. The voids between galaxies, frigid and nearly empty, also convey the history of cosmic evolution. Temperatures here, largely defined by the cosmic microwave background, preserve the low-energy state of matter that has existed since the universe expanded and cooled after the Big Bang. Gas in these regions is sparse, particle collisions are minimal, and chemical reactions occur at glacial rates. Yet the structure and distribution of this matter carry imprints of gravitational evolution, dark matter interactions, and the formation of large-scale structures. Cold stabilizes these signatures, enabling them to persist for billions of years, allowing modern astronomers to detect and interpret the faint evidence of early cosmic dynamics. Even within cold molecular clouds, the history of the universe is encoded in subtle ways. Isotopic ratios, chemical abundances, and molecular complexity all reflect the conditions under which the clouds formed. The influence of nearby supernovae and the primordial processes of element creation. Low temperatures preserve these chemical fingerprints, slowing reactions that might otherwise erase delicate features. Dust grains and ices act as long-term recorders, holding information about cosmic rays, radiation fields, and elemental abundances over astronomical timescales. In these frigid environments, cold functions not just as a stabilizing force, but as a chronicler, allowing the universe to retain a memory of its own past. The earliest stars, the so-called population 3 stars, emerged in an environment dominated by cold gas composed almost entirely of hydrogen and helium. Extreme temperatures in the surrounding medium influenced the rate of collapse, the formation of protostars, and the subsequent ignition of fusion. Cold slowed the motion of atoms, allowed gravitational forces to dominate, and regulated the timescales of formation. Observing the remnants of these processes, whether in faint stellar populations or in molecular clouds enriched by their supernovae, reveals the imprint of the earliest universe. Temperature here is both a regulator and a recorder, controlling physical processes while preserving the conditions of early cosmic evolution. Even in the distant, frigid edges of the observable universe, cold carries information about expansion, matter density, and the evolution of radiation. As the universe expands, temperatures drop, energy becomes diluted, and the baseline cold of space decreases over time. By measuring these temperatures, astronomers can infer the age of the universe, the rate of expansion, and the composition of matter and energy. Cold is not static. It evolves with cosmic time, yet it preserves the memory of prior conditions, encoding the dynamics of creation and evolution within its subtle presence. Cold also interacts with the formation of cosmic structures. Filaments of gas, icy dust grains, and molecular clouds all evolve under the influence of low temperatures, allowing matter to coalesce gradually into stars, clusters, and galaxies. The thermal energy is insufficient to disrupt collapse, preserving the patterns established by gravity and primordial fluctuations. Observing these structures provides insight into the early universe, revealing the interplay between temperature, motion, and density that governed the formation of cosmic architecture. Cold stabilizes, preserves, and regulates, making it both a physical condition and a historical record. Even the faint chemical signatures in the coldest regions of the universe offer clues to the past. Deuterium abundances, molecular hydrogen formation, and complex organics all reflect the conditions of early nucleosynthesis and the first generations of star formation. Cold preserves these signatures, slowing destructive reactions and maintaining structural integrity. By studying these molecules in the frigid interstellar medium, scientists can trace the lineage of matter from the earliest moments of the universe to the present day. Temperature acts as a silent archivist, stabilizing chemical information and allowing it to be deciphered across billions of years. Interstellar ices, another product of extreme cold, capture elements and molecules that might otherwise disperse or react too rapidly. Layers of frozen water, carbon monoxide and methane serve as protective matrices, shielding delicate compounds from radiation and thermal agitation. These ices accumulate over millions of years, preserving a chemical snapshot of the environment at the time of deposition. Cold slows everything down, allowing these frozen archives to exist, offering insight into the processes that governed the early stages of molecular evolution and planetary system formation. Even the behavior of dust grains in these frigid conditions carries historical significance. Tiny particles coated with ices provide surfaces for molecular synthesis and preserve isotopic compositions that reveal the nucleosynthetic history of the galaxy. Cold ensures that these particles remain stable, slowly drifting through molecular clouds and interstellar space, maintaining a record of cosmic conditions that can be read by modern astronomical instruments. Temperature in this way becomes a form of memory, encoding the history of star formation, chemical evolution, and the processes that shaped the universe. Observing the coldest regions of space requires sophisticated instruments. Infrared, submillimeter, and radio telescopes detect the faint thermal emissions of molecules and dust, allowing scientists to infer temperature, density, and motion. These measurements reveal both the present conditions and the historical evolution of matter, demonstrating how cold can preserve information over cosmic timescales. By studying these regions, we learn not only about temperature itself, but about the events and processes it has regulated throughout the history of the universe. Even slight differences in temperature across these ancient regions can reveal the dynamics of the early universe. Warmed filaments, slightly colder cores, and subtle gradients in molecular clouds provide information about gravitational interactions, primordial turbulence, and the distribution of matter in the first billion years. Cold preserves these variations, ensuring that the delicate fingerprints of cosmic history are not erased. Temperature thus serves both as a stabilizing force and a carrier of information, linking the present universe to its earliest moments. Ultimately, extreme cold offers a lens through which we can study the origin and evolution of the cosmos. From the pervasive cosmic microwave background to frigid molecular clouds, from icy dust grains to the remote voids between galaxies, temperature preserves, regulates, and records the history of the universe. Cold slows motion, stabilizes matter, enables chemical complexity, and governs the formation of stars and planets. It acts as both a physical and historical force, connecting the past to the present and allowing us to interpret the subtle signals left by billions of years of cosmic evolution. In contemplating these frozen archives, it becomes clear that cold is much more than an environmental condition. It is a storyteller, encoding the narrative of the universe in molecules, dust, radiation, and motion. By studying the coldest places in space, we are, in essence, reading the history of the cosmos, tracing the sequence of events from the aftermath of the Big Bang to the formation of the first stars, the assembly of galaxies, and the chemical evolution that ultimately enabled planetary systems like our own to emerge. Temperature, in its quiet, pervasive presence, is both measure and memory, linking all processes across space and time in a subtle, enduring embrace. In contemplating the vast stretches of space, where temperatures plunge far below anything we experience on Earth, a sense of perspective emerges, both humbling and quietly reassuring. We find ourselves in a universe defined as much by cold as by light, where interstellar clouds drift in icy silence, molecular compounds linger frozen for eons, and entire galaxies are immersed in the faint glow of the cosmic microwave background. The cold is pervasive, yet it is neither threatening nor empty. It is a condition that structures matter, preserves history, and enables the slow, deliberate evolution of stars, planets, and chemical complexity. Reflecting on our place in this frozen cosmos invites us to appreciate the extraordinary balance between warmth and chill, activity and stillness, energy and preservation that governs the universe. Even in regions that seem desolate, such as the voids between galaxies, cold is a quiet architect, ensuring stability and continuity across unimaginable distances. Matter drifts slowly, collisions are rare, and energy exchanges are subtle. Yet gravity and cold together orchestrate the formation of filaments, the coalescence of gas, and the long-term evolution of structure. For any observer, the sheer scale of these processes is staggering. The universe expands, temperatures fall, and yet matter arranges itself in ways that are precise and orderly. Cold, in this sense, is a sculptor, working in slow motion, invisible yet profoundly influential, shaping the rhythm of cosmic evolution. Within molecular clouds and Bok globules, cold governs both chemistry and motion. Icy dust grains provide surfaces for molecules to form and interact, while low temperatures preserve these structures over millions of years. Gravity acts patiently, pulling matter into dense cores that will eventually ignite as stars, while surrounding cold gas stabilizes the environment. Cold controls the pace of these processes, ensuring that matter evolves slowly, deliberately, and predictably. Without the chill of these environments, the complex interplay between physics and chemistry that produces stars and planets would be disrupted. The extreme cold acts as both a guide and a stabilizer, shaping the emergence of structure from apparent emptiness. Even our own solar system provides lessons about the power of cold. The icy moons of Jupiter and Saturn, the distant dwarf planets of the Kuiper Belt, and the shadowed craters of Mercury reveal how low temperatures govern surface and atmospheric behavior. Volatile compounds remain frozen, chemical reactions proceed slowly, and subtle geological features are preserved for millions or billions of years. Cold maintains equilibrium, moderates change, and protects the potential for future activity, whether that be geysers on Enceladus, the shifting ices of Pluto, or the slow sublimation of frozen methane and nitrogen. The chill of these worlds is a quiet force, shaping planetary evolution and preserving evidence of past events. Interstellar space extends this lesson on a cosmic scale. The voids between stars and galaxies, bathed in the faint glow of the cosmic microwave background, are cold to the point of near inertia. Here, atoms drift for millions of years with minimal motion. Collisions are infrequent, and energy transfer occurs only through subtle radiative processes. Cold preserves the state of matter over immense distances and timescales, allowing it to carry the imprint of cosmic history. From the remnants of the Big Bang to the formation of galaxies, temperature provides continuity, enabling matter to evolve gradually while maintaining the structure necessary for stars and planets to emerge. Even the paradoxical cold of black holes in the Boomerang Nebula underscores the universality of extreme chill. While black holes contain vast gravitational energy, their Hawking radiation corresponds to temperatures near absolute zero, demonstrating that immense energy content does not preclude extreme cold. The Boomerang Nebula achieves temperatures below the cosmic microwave background through rapid expansion, showing how dynamics and cold can combine to produce extraordinary conditions. These examples reveal that cold is not merely the absence of heat. It is a governing principle, influencing energy, motion, and chemical evolution across a broad range of scales and contexts. Observing these frigid regions allows us to glimpse the history of the universe. The faint emissions from molecules, the delicate ice mantles on dust grains, and the subtle glow of radiation in near-empty space all carry information about the past. Cold preserves this information, ensuring that chemical signatures, density fluctuations, and motion patterns remain detectable over billions of years. By studying these environments, astronomers can reconstruct the sequence of events that led to the formation of stars, planets, and galaxies, using temperature itself as both a measure and a memory of cosmic evolution. Even in the laboratory, where scientists recreate aspects of extreme cold through cryogenics, the principles observed mirror those found in the cosmos. Superfluidity, Bose-Einstein condensates, and slow chemical reactions all reveal the subtle interplay between temperature, motion, and structure. These experiments provide insight into the fundamental behavior of matter at near-zero temperatures and allow us to understand how cold can regulate processes on both microscopic and cosmic scales. Cold is not passive. It is a force that guides, preserves, and reveals the principles governing matter, from atoms in a laboratory to interstellar clouds across light years. The role of cold in star and planet formation also illustrates its creative power. By slowing motion, stabilizing matter, and enabling chemical reactions to occur gradually, extreme chill ensures that stars ignite, planetary disks form, and complex molecules accumulate. Cold shapes the distribution of mass, the composition of planets, and the potential for habitable environments. It is both protective and generative, ensuring that the universe can evolve in an orderly, predictable manner while leaving room for complexity, diversity, and emergent behavior. Even in the early universe, cold preserved the imprint of structure and chemical composition. The cosmic microwave background and the faint signals from primordial clouds carry information about density fluctuations, gravitational interactions, and the distribution of matter shortly after the Big Bang. Temperature in these regions dictated the rate of particle motion, the survival of molecules, and the emergence of structure. Cold, in effect, acted as both historian and regulator, capturing a snapshot of the universe in its earliest moments while guiding its subsequent evolution. Intergalactic space, with its extreme low density and pervasive cold, further emphasizes the importance of temperature in cosmic evolution. Matter drifts slowly, gravitational interactions shape filaments and voids, and energy transfer occurs only through subtle radiation. Cold maintains stability across immense scales, allowing structures to emerge, persist, and evolve. It preserves the faint chemical and isotopic signatures of cosmic history, making intergalactic space both a silent witness and a slow-moving laboratory of time, where the chill dictates the pace of evolution and the preservation of matter. Even as we consider the frozen worlds of our solar system, the dynamics of molecular clouds, and the chilling extremes of intergalactic space, a theme becomes clear. Cold is not simply a physical condition. It is a regulator, a preserver, and a storyteller. Temperature shapes motion, controls chemical reactions, maintains structure, and records history across scales ranging from microscopic molecules to entire galaxies. By observing, modelling, and understanding cold, we gain insight into the processes that have shaped the universe, the evolution of matter, and the conditions that have ultimately allowed stars, planets, and life to emerge. Reflecting on our place in this frozen cosmos reveals a delicate balance. The warmth of stars, the heat generated by geological processes, and the radiation of active galaxies coexist with pervasive cold, extreme chill, and near absolute zero environments. Cold is not a hindrance. It is a necessary condition, ensuring stability, preserving complexity, and regulating the pace of evolution. It allows matter to accumulate, molecules to survive, and stars and planets to form in a precise, predictable manner. In understanding cold, we understand the universe itself and our own small place within it. Even on a personal level, considering the cold expanses of space invites a contemplative perspective. The vast, icy reaches between stars and galaxies, the frozen surfaces of distant worlds, and the extreme low temperatures of molecular clouds and nebulae all remind us of the patience and scale of cosmic processes. Cold is pervasive, shaping every corner of the universe, yet it is subtle, quiet, and almost imperceptible to human senses. By appreciating this chill, we connect with the slow, deliberate rhythms of the cosmos and gain a sense of continuity, stability, and wonder. Cold in the universe is both functional and poetic. It preserves, stabilizes, regulates, and communicates across time and space. From the icy voids between galaxies to the frozen surfaces of distant moons, from the extreme chill of the Boomerang Nebula to the delicate chemistry of molecular clouds, cold is essential to the emergence, evolution, and structure of the cosmos. In this silent, pervasive temperature, the universe encodes its history, governs its present, and prepares for its future, inviting us to reflect on our own place within the vast, frozen expanse. As we slowly drift back from the farthest, coldest corners of the universe, a quiet sense of awe emerges, accompanied by a gentle realization of how profoundly cold shapes every corner of existence, from the tiny icy dust grains in molecular clouds to the frozen moons at the edges of our solar system, from the frigid expanses of intergalactic space to the nearly absolute zero temperatures of the Boomerang Nebula. The universe is a symphony orchestrated by extreme chill. This pervasive cold is subtle, often invisible, yet it is everywhere, regulating motion, preserving molecules, guiding formation, and maintaining the delicate balance required for stars, planets, and galaxies to exist. In embracing the beauty of cosmic chill, we begin to understand the elegance of the universe itself. The role of cold is both creative and protective. Within molecular clouds, it slows atomic motion, allowing gravity to assemble matter into dense cores, the seeds of future stars. Chemical reactions proceed slowly, preserving delicate molecules that may one day become part of planets, or even the precursors to life. In globules, the frigid isolation ensures stability, while matter is organized meticulously over millions of years. Even in the Boomerang Nebula, where expansion-driven cooling produces temperatures lower than the cosmic microwave background, cold demonstrates its extraordinary ability to dominate dynamics, influencing the behavior of particles and preserving matter at levels almost inconceivable to our daily experience. Cold is patient, deliberate, and profoundly influential, quietly sculpting the cosmos across unimaginable spans of space and time. Every frozen world within our solar system illustrates the subtlety and power of low temperatures. Icy moons like Europa and Enceladus hold subsurface oceans beneath layers of ice, preserved by extreme cold from the frigid vacuum of space. Dwarf planets and Kuiper belt objects, covered in nitrogen and methane ices, maintain chemical and geological records dating back billions of years. Even Mercury's shadowed polar craters act as reservoirs of water ice, their preservation dependent entirely on chill and darkness. Cold here regulates processes, stabilizes matter, and maintains conditions that allow geological and chemical evolution to unfold over timescales that dwarf human history. It is both a foundation and a framework, shaping planetary environments with subtle yet relentless influence. Looking outward to intergalactic space, the same principles hold on scales that challenge imagination. Between galaxies, matter drifts almost entirely unimpeded, subject to the pervasive temperature of the cosmic microwave background. Collisions are rare, molecular motion is minimal, and energy exchanges occur primarily through the faintest radiation. Cold ensures the stability of these vast regions, allowing gravity to shape filaments and voids that compose the cosmic web. Here, extreme chill preserves the structure of the universe, enabling subtle processes to accumulate across billions of years. Cold is not empty or inert. It is active, regulating the evolution of matter, the distribution of energy, and the emergence of structure on the grandest scales imaginable. The paradox of temperature in black holes further illuminates the beauty of cosmic chill. These objects, containing immense energy and mass, can radiate at temperatures approaching absolute zero, illustrating that cold and energy are not mutually exclusive. Hawking radiation is faint, almost imperceptible, yet it reveals that even extreme environments operate under rules in which chill plays a central role. Temperature, here, becomes a nuanced concept, integrating energy, gravity, and quantum mechanics, demonstrating that cold can coexist with profound dynamism. Even the objects that seem most destructive and powerful in the universe are bound by the principles of temperature, motion, and thermal balance. Cold also serves as a window into history. The cosmic microwave background, the faint afterglow of the Big Bang, preserves the temperature, density, and motion of the universe at its infancy. Molecular clouds hold chemical signatures that date back billions of years, and icy grains in dark molecular clouds archive the elemental and isotopic composition of primordial matter. By studying these regions, scientists trace the formation of stars, the assembly of galaxies, and the evolution of chemical complexity. Cold is not simply a present condition. It is a recorder, preserving memory across space and time, enabling us to read the story of the universe through temperature itself. Even in the laboratory, the influence of extreme cold mirrors cosmic conditions, linking human understanding with universal processes. Cryogenic experiments recreate temperatures near absolute zero, producing superfluids, Bose-Einstein condensates, and exotic states of matter that illustrate the subtle physics governing the universe. By observing these systems, we gain insight into molecular behavior, quantum effects, and the slow, deliberate evolution of matter that unfolds over vast scales. Cold connects the human and the cosmic, the experimental and the observational, revealing a continuity of principles that stretches from earthbound laboratories to the farthest reaches of space. The formation of stars and planets depends intrinsically on chill. In frigid molecular clouds, gravity draws matter into dense cores, while low temperatures prevent thermal pressure from dispersing material. Ices accumulate on dust grains in protoplanetary disks, forming the building blocks of planets, moons, and comets. Cold preserves volatile compounds, controls motion, and regulates energy transfer, ensuring that the delicate interplay between physics and chemistry produces stable, structured systems. Without this pervasive cold, the universe would lack the ordered complexity that allows galaxies, stars, and planetary systems to emerge. Cold is both a foundation and a conductor, orchestrating the evolution of matter in deliberate, measured ways. Reflecting on the frozen worlds of our solar system, the icy interstellar clouds, and the near-absolute zero temperatures of extreme cosmic environments, it becomes clear that cold is both subtle and profound. It stabilizes, preserves, regulates, and enables, shaping every process it touches. Even in the apparent emptiness of intergalactic space, extreme chill maintains order, guides accumulation, and preserves memory. From the faint motion of particles to the assembly of stars and planets, cold is a constant, silent participant in the unfolding of cosmic evolution. It is pervasive, patient, and essential. Even the human perspective benefits from contemplating this universal cold. Recognizing the intricate ways in which temperature governs cosmic processes allows us to situate ourselves within a vast, structured, and delicately balanced universe. The stars we see, the planets we inhabit, and the chemical elements that compose our bodies all emerged under the subtle guidance of extreme chill. Cold is the quiet companion to creation, the regulator of evolution, and the preserver of structure, linking the earliest moments of the universe to the conditions we observe today. Cold is also a reminder of continuity. From the first atoms forming after the Big Bang to the icy cradles of future stars, the principle remains the same. Low temperatures, slow motion, preserve chemical complexity, stabilize structures, and allow gravitational forces to act over vast timescales. Every icy moon, molecular cloud, and distant nebula is a testament to the enduring role of temperature in shaping the universe. Cold is both timeless and universal, connecting the smallest grains of ice to the largest structures in the cosmos. Even as we conclude our exploration, the beauty of cosmic chill lingers. It is subtle, nearly invisible, yet profoundly influential. It preserves the past, structures the present, and shapes the future. Cold allows the universe to evolve with patience and precision, enabling the formation of stars, planets, and chemical diversity, while maintaining stability across incomprehensible scales. In contemplating the pervasive chill that threads through every corner of space, we find a sense of wonder, tranquility, and perspective, appreciating the silent force that underpins the universe. Ultimately, the beauty of cosmic chill lies in its quiet power. It is not violent or dramatic, yet it shapes the evolution of the universe in fundamental ways. It governs motion, preserves chemical integrity, regulates energy transfer, and records the history of cosmic events. From icy moons and distant dwarf planets to the depths of intergalactic space and the frigid extremes of nebulae, cold is a constant presence, a stabilizing and generative force. Recognizing its role allows us to understand the universe more deeply, appreciating the elegance and subtlety of a cosmos that moves slowly, deliberately, and in harmony with the principles of temperature and matter. As we drift away from this exploration, a calm realization emerges. The universe is a balance of extremes, where light and cold coexist, where energy and stillness interact, and where temperature shapes every process. Cosmic chill is not emptiness. It is structure, preservation, and possibility. It is the quiet stage upon which the drama of creation unfolds, the patient architect of matter, and the subtle narrator of the universe's long unfolding story. In contemplating this chill, we gain not only knowledge, but also a serene connection to the cosmos, a sense of our place within a universe shaped by extreme temperatures, quiet persistence, and the delicate beauty of cosmic order.